Hello and welcome. Tonight, we're going to drift together through space. Not the kind you need a rocket to reach, but the kind you can explore from right where you are, letting your mind wander among stars and galaxies while your body settles into rest. If you enjoyed this journey, consider subscribing to the channel. There are many more cosmic mysteries waiting for you. Now, let's begin. There's an invisible line drawn across the sky, 62 miles above your head. We call it the Kármán line, and it marks the place where Earth's atmosphere becomes so thin that conventional aircraft can no longer fly. The place where space, officially, begins. 62 miles. That's closer than you might think. It's the distance between some neighbouring cities. A drive you could make in an hour if the road went straight up instead of winding along the ground. You could point at the sky and say, space starts just over there, and in a cosmic sense, you wouldn't be wrong. We think of space as impossibly distant, something reserved for astronauts and billion-dollar rockets, but really it's just overhead, a short journey away, separated from your breakfast table by nothing more than air that gets thinner and thinner the higher you go. Of course, getting there is another matter entirely. You can't simply climb, but the boundary itself? It's waiting, quiet and patient, closer than the horizon. Look up on a clear night, and you might see a few thousand stars if you're lucky enough to be far from city lights. But those stars, every single one you can see with your naked eye, belong to just one galaxy. Our galaxy, the Milky Way, and the universe contains an estimated 2 trillion galaxies. 2 trillion. Each one a city of stars, each one containing billions or even trillions of suns, many with their own planets, their own moons, their own quiet corners where perhaps something stirs and wonders about the cosmos just as we do. If you started counting galaxies, one per second, never stopping to sleep or eat or rest, it would take you more than 60,000 years to count them all. 60,000 years of counting, and you'd only be tallying the ones we can see. The observable universe, the portion of existence whose light has had time to reach us. There may be more beyond, there probably are, but those galaxies are so far away that their light hasn't arrived yet, and maybe it never will. 2 trillion galaxies. It's a number that dissolves meaning, that turns the mind soft and quiet. And somewhere in all that vastness, here you are, listening to this, breathing in and out. You might think of space as perfectly empty, a void, a vacuum, a nothing stretched across everything. And in many ways, you'd be right. Space is emptier than anything we can create on Earth, emptier than the best vacuum chambers in our most sophisticated laboratories. But it's not completely empty. On average, every cubic centimetre of space contains about 1 atom, just one. A single hydrogen atom most likely drifting alone through the dark. It doesn't sound like much, and it isn't. 1 atom in a volume the size of a sugar cube. But it's something. Space, in its own way, is populated. Thinly, yes. Sparsely beyond comprehension. But not utterly barren. In our laboratories, and we can pump air out of a chamber and create a vacuum, but there are always a few stubborn molecules clinging to the walls, bouncing around inside. We can't get rid of them all. Space, somehow, is better at being empty than we are at making emptiness, and yet, even space holds on to these lone atoms, scattered like seeds across an infinite field, waiting for gravity to gather them together into clouds, into stars, into worlds. Nothing is ever truly nothing, it seems. Even the vacuum hums with potential. Right now, about 250 miles above your head, The International Space Station is screaming through the sky at 17,500 miles per hour. That's nearly 5 miles every second, fast enough to circle the entire Earth in just 90 minutes. Imagine that. 90 minutes for a complete orbit. The astronauts aboard don't experience day and night the way we do, with the slow turn of the Earth bringing gradual transitions from dawn to noon to dusk. Instead, they watch the sun rise, arc across the sky, and set again in the span of 45 minutes. Then darkness, then another sunrise. 16 times a day they see the sun climb over the horizon. 16 sunsets painting the thin blue line of Earth's atmosphere in shades of orange and red. It's a strange way to live, untethered from the rhythm that has governed life on this planet for billions of years. No morning that stretches into afternoon, no evening that deepens into night. Just this constant cycling, this endless loop of light and shadow over and over as the station hurtles through the void. And through the windows, Earth turns below, blue and white and brown. A marble suspended in black, rotating slowly beneath them while they race around it at a speed no human body was ever designed to travel. They're falling, really. Falling toward Earth, but moving so fast sideways that they keep missing it. That's what an orbit is, a continuous fall that never ends. When you look at the sun, though you shouldn't, not directly, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago. Light's fast, unimaginably fast. It travels at 186,000 miles every second, crossing distances that would take us lifetimes in the blink of an eye. And yet, even at that speed, even racing through the vacuum at the universe's ultimate speed limit, light from the sun takes more than 8 minutes to reach us. 8 minutes, long enough to boil an egg, or long enough to listen to 2 songs, long enough that if the sun suddenly vanished, if some cosmic hand reached in and snuffed it out like a candle, we wouldn't know. We'd keep living our lives, feeling the warmth on our skin, seeing the light streaming through our windows, completely unaware that the source of all that light and warmth was already gone. For 8 minutes and 20 seconds, we'd continue in a world that no longer existed, living in the past without knowing it. And it's not just the sun. Every star you see is a ghost, a memory, a light that left its source years or centuries or millennia ago. The night sky is a museum of history, and we are its visitors, looking back in time with every glance upward. The moon is leaving us, not quickly, not noticeably, not in any way you'd see over the course of your lifetime or even over the course of human civilization. But every year, the moon drifts about 1.5 inches farther from Earth, pulled slowly away by the same tidal forces that cause the oceans to rise and fall. 1.5 inches, a distance smaller than the length of your thumb. But it adds up. 1 billion years ago, the moon was much closer, so close that it loomed enormous in the sky, appearing 3 times larger than it does now. And back then, Earth spun faster. A day lasted only 5 hours. 5 hours of light, 5 hours of darkness, the planet whirling beneath a giant moon that hung overhead like a watching eye. Slowly, the moon's gravity has been pulling on Earth's oceans, creating friction, slowing our spin. And in return, Earth's gravity has been pushing the moon away, giving it energy, sending it farther and farther into the dark. One day, billions of years from now, long after we're gone, the moon will be so far away that it will no longer create total solar eclipses. The cosmic coincidence that makes our moon appear exactly the same size as the sun in our sky will end. The moon will shrink, become a smaller disk, and the shadows it casts will no longer be quite as perfect. But for now, for this brief moment in cosmic time, we get to see them aligned. We get to stand in the moon's shadow and watch the sun's corona flare around its edges. A gift of timing, of being here, now, while the distance is just right. Venus is the hottest planet in our solar system, even though Mercury is closer to the Sun. You'd think proximity would matter most, that the nearest world to our star would bear the most heat. But temperature, it turns out, is more complicated than distance. Venus has an atmosphere, a thick one, so thick that the air pressure at its surface is 90 times greater than Earth's, like being half a mile underwater, and that atmosphere is made almost entirely of carbon dioxide, a greenhouse gas that traps heat with ruthless efficiency. Sunlight filters down through Venus's clouds, warming the surface. But when that surface tries to radiate heat back into space, the carbon dioxide stops it, holds it, reflects it back down. The heat builds and builds and builds until the surface reaches 900 degrees Fahrenheit, hot enough to melt lead, hot enough to glow a dull red in the darkness. It's a runaway greenhouse effect, a cautionary tale written in planetary physics. Venus might have once been more like Earth, cooler, with liquid water on its surface, perhaps even the conditions for life. But something went wrong. The atmosphere thickened, the heat climbed, the oceans boiled away, and the water vapor, itself a greenhouse gas, made everything worse, trapping even more heat, until Venus became the inferno it is today. Now it's a world of sulfuric acid clouds and crushing pressure and temperatures that would vaporize a human being in seconds. A warning, maybe, of what can happen when a planet's climate spirals out of control, or simply a reminder that not every world is meant to be a home. Here's something strange. On Venus, a day is longer than a year. It takes Venus 225 Earth days to complete one orbit around the Sun. That's its year, the time it takes to make one full journey around our star. But it takes 243 Earth days for Venus to rotate once on its axis. That's its day, the time from one sunrise to the next. So a Venusian year passes before a Venusian day is finished. The planet completes its orbit before it completes a single spin. And there's more. Venus rotates backward, clockwise when viewed from above, while almost every other planet in the solar system rotates counterclockwise. We call this retrograde rotation, and it means that if you could somehow stand on Venus's surface without being crushed or melted, you'd see the sun rise in the west and set in the east, the opposite of what we experience here on Earth. Why? We're not entirely sure. The best guess is that Venus suffered a massive collision early in its history. A glancing blow from another planet or a large asteroid that knocked it sideways, it slowed its rotation, maybe even reversed it. A violent beginning for a planet that's now one of the brightest objects in our sky. The evening star that's not a star at all, but a world spinning slowly backward through the dark. On Jupiter, there's a storm that's been raging for at least 400 years. We call it the Great Red Spot, though it's more orange than red these days. A swirling anticyclonic hurricane large enough to swallow 3 Earths whole. 400 years. When Galileo first turned his telescope toward Jupiter in the early 1600s, this storm might have already been there, churning in the planet's atmosphere, though we can't be sure. The first confirmed observations came in the 1800s, and ever since, we've watched it spin. A vast oval of clouds rotating counterclockwise. driven by winds that howl at hundreds of miles per hour. It's been shrinking though, slowly. Images from the 1800s show a storm nearly twice as large as it is now, and modern observations reveal that it's still getting smaller, though we don't fully understand why. Maybe it's running out of energy. Maybe the dynamics of Jupiter's atmosphere have shifted in ways we haven't detected yet. Or maybe the storm is just dying, the way all storms eventually do, and in another century or two the great red spot will fade and vanish, leaving Jupiter's face smooth and unmarked. For now it endures, a feature so large you can see it through a backyard telescope, a reminder that weather on other worlds operates on scales we can barely comprehend. 400 years of continuous wind and cloud and chaos, a storm that predates nations, that has outlived empires, that has turned and turned while humans built cities and fought wars and reached for the stars. Saturn's rings are perhaps the most beautiful structures in the solar system. Thin, bright, impossibly delicate bands encircling the planet like a halo. From a distance, they look solid, like a disk of polished ice. But up close, they reveal themselves as billions upon billions of individual chunks, ice and rock, ranging in size from grains of dust to houses, each one orbiting Saturn on its own trajectory. And they're thin, astonishingly thin. In some places, the rings are only 30 feet thick, about the height of a 3-story building. Imagine a structure tens of thousands of miles across, but only as tall as a house. If you scaled Saturn's rings down to the size of a piece of paper, they'd be thousands of times thinner than that paper. They're more gap than substance, more space than matter. We don't know exactly how old they are. They might be ancient, formed when Saturn itself was born, remnants of a moon that wandered too close and was torn apart by tidal forces. Or they might be young, cosmically speaking, perhaps only a few 100 million years old, the debris from a shattered comet or a collision between moons. Either way, they won't last forever. Slowly, imperceptibly, the rings are falling. Ice particles spiral inward, drawn by Saturn's gravity, raining down onto the planet's atmosphere in what scientists call ring rain. In another 100 million years, maybe less, the rings will be gone, dissolved, absorbed, lost to time, but for now, they're here, fragile and fleeting and impossibly beautiful, and catching the sunlight and scattering it back into the dark. Uranus rolls through space on its side, tilted at 98 degrees to its orbital plane, nearly perpendicular to the way most planets spin. Imagine Earth tilted so far over that the North Pole pointed directly at the Sun. That's Uranus. We think a collision did this. Early in the solar system's history, when planets were still forming and the neighbourhood was crowded with debris, something massive, perhaps another planet, perhaps a body the size of Earth, slammed into Uranus with enough force to knock it sideways. The impact didn't destroy the planet, but it fundamentally changed its orientation, leaving it to tumble through space in a configuration unlike anything else we know. This tilt creates the strangest seasons in the solar system. For 21 years, Uranus's north pole faces the sun, bathing the northern hemisphere in continuous daylight, while the southern hemisphere languishes in endless night. Then, as the planet continues its 84-year orbit, the seasons shift. The sun climbs higher, crosses the equator, and for the next 21 years, it's the south that basks in light while the north freezes in darkness. 21 years of summer, 21 years of winter. No quick transitions, no gentle spring or autumn, just long, slow cycles of light and dark, warmth and cold, playing out over decades beneath skies filled with methane clouds and winds we're only beginning to understand. It's a world knocked askew, forever spinning sideways, a reminder that the universe doesn't always follow the patterns we expect. Neptune is the farthest planet from the Sun, a cold, a blue world more than 2.5 billion miles away, where sunlight arrives 900 times weaker than it does on Earth. You'd think a planet so distant, so starved of solar energy, would be quiet, calm, frozen into stillness. But Neptune has the fastest winds in the solar system, 1,200 miles per hour, supersonic winds that scream through the planet's atmosphere, whipping clouds of methane ice into enormous storm systems that dwarf anything we see on Earth. The winds are so fast they break the speed of sound. Not that sound travels well in Neptune's thin, frigid air, but the comparison gives you a sense of the violence, the raw kinetic energy tearing through that distant sky. We don't entirely understand why. Neptune receives almost no heat from the Sun, so where does all this energy come from? And the best explanation we have is that Neptune generates its own heat, radiating more energy than it absorbs, leftover warmth from its formation perhaps, or heat produced by the slow settling of heavier elements deep in its interior. This internal furnace drives convection currents, and those currents, combined with the planet's rapid rotation, create winds that make Earth's hurricanes look gentle by comparison. It's a strange thought. A world so far from the Sun that it barely feels its warmth, and yet so active, so turbulent, churning with storms that have raged for longer than human civilization has existed. Distance doesn't always mean stillness. Sometimes it just means isolation, a world left to its own devices, spinning and storming in the dark. There are more stars in the universe than grains of sand on all of Earth's beaches. It's one of those facts that sounds like hyperbole, like poetic exaggeration. But the math supports it. If you gathered every grain of sand from every beach, every desert, every sandbox and shoreline on the planet, you'd have somewhere around 7 quintillion grains, a number with 18 zeros. The universe contains more stars than that, far more. By some estimates, there are around 1 septillion stars, a number with 24 zeros, maybe more. We're not great at counting things we can't see directly, and most stars are too faint, too distant, too hidden behind dust clouds for us to detect individually. But based on the galaxies we can observe, and the average number of stars each galaxy seems to hold, the numbers climb into the incomprehensible. And yet, for all those stars, the universe is still mostly empty. Yet the distances between them are so vast that if you were standing on a planet orbiting one star, the nearest star might be light years away, so far that its light would take years to reach you, travelling at a speed nothing else can match. More stars than sand, more space than stars. The universe is a paradox of abundance and emptiness, crowded and lonely all at once. The Sun is not just the centre of our solar system, it's almost the entire solar system. 99.86% of all the mass in our solar system belongs to the Sun. Everything else, all the planets, all the moons, all the asteroids and comets and dust grains, every piece of rock and ice and metal orbiting through the darkness, accounts for just 0.14%. Jupiter, the largest planet, holds most of that remaining mass. Saturn takes a portion. The rest of us, Earth, Mars, Venus, all the smaller bodies, are rounding errors, cosmic afterthoughts, tiny flecks of matter clinging to the edges of the sun's gravitational well. It's humbling in a way. We think of the solar system as a collection of worlds, each one important, each one worthy of study and wonder. And they are. But in terms of sheer mass, in terms of gravitational dominance, there's really only one object that matters: the sun. Everything else is just debris, leftovers from the cloud of gas and dust that collapsed to form our star 4.5 billion years ago. The sun took the lion's share, we got the scraps, and yet those scraps include Earth. They include life, they include you listening to this, made of atoms that once drifted in that primordial cloud, is now gathered into something that can think and wonder and look back at the star that made it all possible. Neutron stars are the collapsed cores of massive stars, the remnants left behind after a supernova tears a star apart. What remains is a sphere about 12 miles across, roughly the size of a city, but containing more mass than the sun. The density is almost impossible to comprehend. If you could take a teaspoon of neutron star material and bring it to Earth, it would weigh about 6 billion tons. 6 billion tons in a volume the size of a sugar cube. It would sink through the ground like it wasn't there, plunging toward the center of the planet, pulled by its own impossible weight. Inside a neutron star, matter is compressed so tightly that atoms collapse. Electrons and protons merge to form neutrons, and those neutrons pack together in configurations we can barely simulate in our laboratories. The core might contain exotic states of matter, quark soup, superfluid neutrons, things that exist nowhere else in the universe. The surface, if you can call it that, is solid. A crust of iron nuclei packed into a crystalline lattice, smooth and unimaginably hard. If you could somehow stand on a neutron star, though you couldn't, the gravity would flatten you into a layer of atoms. You'd find yourself on the smoothest surface in the universe, with irregularities measured in millimeters across a sphere 12 miles wide. And beneath your feet, the core would hum with pressures greater than anything we can create, with forces that distort space-time itself, pulling and warping the fabric of reality into shapes our equations struggle to describe. Some neutron stars spin. Not slowly, not in the stately rotation of planets or ordinary stars, but hundreds of times per second. So fast they become cosmic strobe lights, pulsing radiation into space with clockwork precision. We call them pulsars. They form when a massive star collapses into a neutron star, and conservation of angular momentum causes the collapse to spin faster and faster, like a figure skater pulling in their arms. The star's magnetic field collapses too, concentrating and amplifying until it becomes trillions of times stronger than Earth's. Charged particles spiral along the magnetic field lines, accelerating to near light speed, and where they escape at the magnetic poles, they create beams of radiation, radio waves, X-rays, gamma rays, that sweep through space like lighthouse beams. If one of those beams happens to point toward Earth, we see a pulse, then another, ticking away with such regularity that when astronomers first discovered pulsars in 1967, they briefly wondered if they detected signals from an alien civilization. They even nicknamed the first one LGM-1 for Little Green Men. But no, not aliens, just physics. Just a dead star spinning in the dark, its magnetic field screaming into the void, sending out pulses that travel for hundreds or thousands of light years before reaching our telescopes. Some pulsars keep time more accurately than atomic clocks. They're so stable, so precise, that astronomers have seriously considered using them as navigation beacons for spacecraft. Cosmic GPS satellites, built not by engineers but by the violent deaths of stars. The coldest place in the universe that we know of isn't in the depths of intergalactic space. It's the Boomerang Nebula, a cloud of gas about 5,000 light-years from Earth, where temperatures drop to minus 458 degrees Fahrenheit. That's just 1 degree above absolute zero, the theoretical lowest temperature possible, the point at which atoms barely move at all. The Boomerang Nebula is colder than the cosmic microwave background, colder than the radiation left over from the Big Bang that permeates all of space. How is that possible? How can something be colder than the universe itself? The answer lies in the nebula's expansion. At its centre, a dying star is shedding its outer layers, blowing gas into space at hundreds of thousands of miles per hour. As that gas expands, it cools, the same principle that makes a compressed air canister feel cold when you spray it. But in the Boomerang Nebula, the expansion is so rapid, so violent, that the cooling exceeds the warming from the cosmic background radiation. For a brief time, cosmically speaking, this nebula holds the record. The coldest known place, a frozen remnant of a dying star, colder than the void between galaxies, colder than the empty reaches where no light has ever shone. Eventually it will warm up. The expansion will slow. The universe's background heat will seep in. But for now, the Boomerang Nebula drifts through space, a frigid monument to the strange physics of stellar death. Space has a smell, or rather, things that have been in space carry a smell back with them. Astronauts who've performed spacewalks report a distinctive odour clinging to their suits when they return to the airlock. A scent like seared steak, hot metal, welding fumes, burnt gunpowder. Sharp, metallic, unforgettable. No one has actually smelled space directly. You can't exactly take your helmet off for a sniff, but the scent transfers. High-energy particles, ionized atoms, polycyclic aromatic hydrocarbons created by dying stars and scattered through the cosmos. All of these cling to the fabric of spacesuits, and when the airlock repressurizes, the smell becomes noticeable. It's the smell of chemistry happening at extreme energies, of atoms stripped of electrons and recombining in unusual ways, of the cosmic environment leaving its fingerprint on everything it touches. Some astronauts find it pleasant. Others describe it as acrid, unpleasant, like a factory or a foundry. But all agree, space has a scent, even if we can only experience it second-hand, filtered through the materials we use to protect ourselves from the void. It makes you wonder what else we're missing. What other sensations does space hold that we can't detect, can't experience, because we're sealed inside our suits and ships, separated from the environment by layers of metal and fabric and air? What does the solar wind feel like? What sound would a nebula make if sound could travel through vacuum? We'll probably never know, but at least we know what space smells like. Hot metal and burnt stardust, the scent of the cosmos itself. Deep in the constellation Sagittarius, about 26,000 light-years from Earth, there's a cloud of gas and dust called Sagittarius B2. It's a star-forming region, a place where gravity is slowly gathering matter together, compressing it, heating it, preparing to ignite new suns, and it contains enough ethanol, ordinary drinking alcohol, to fill 400 trillion pints of beer. 400 trillion. A number so large it loses meaning. If every person on Earth drank a pint of beer every day for the rest of their lives, and then their children did the same, and their children's children, on and on for billions of years, we wouldn't make a dent in the supply. The alcohol isn't there for any grand reason. It forms through ordinary chemical reactions, carbon and oxygen and hydrogen combining in the cold darkness, creating complex organic molecules that drift through space until they're incorporated into new stars or planets, or perhaps someday life. And it's not just alcohol. Sagittarius B2 also contains ethyl formate, the chemical that gives raspberries their flavour, and ethyl methanoate, which smells like rum. The cloud is, in a very real sense, a cosmic distillery, brewing vast quantities of organic compounds in the cold between stars. It's a reminder that space isn't sterile, it's not empty and lifeless, it's full of chemistry, full of the building blocks of complexity, scattered across light years, waiting for gravity to gather them into something new. When the Apollo astronauts walked on the moon, they left footprints in the dust, deep clear impressions, boot treads pressed into the fine grey regolith, marking the places where humans first walked on another world. Those footprints are still there. They'll likely remain for millions of years. On Earth, footprints in sand or mud last hours, maybe days. Worry, before wind or rain or the movement of animals erases them. But the moon has no wind, no rain, no weather at all really, just the slow, patient bombardment of micrometeorites and the gentle push of solar radiation. Erosion happens on the moon, but it's slow. Geological processes measured in millions of years instead of seasons. The footprints will blur eventually. Tiny impacts will chip away at their edges. Dust will settle into the depressions, grain by grain. But the process is so gradual that for now, for the foreseeable future, those marks endure. Neil Armstrong's first step, Buzz Aldrin's boot prints beside the lunar module, the tracks left by the rovers, the spots where equipment was placed and later moved. All of it preserved, frozen in time, a record of humanity's brief visit to a world that doesn't change the way Earth does. It's a strange kind of immortality, not in memory, not in monuments built by human hands, but in the simple physics of a lifeless world where nothing erodes, nothing grows, nothing moves except what we put there. Someday, maybe, someone will return and see those footprints. Maybe they'll stand beside them, comparing the old prints to their own. Or maybe the moon will remain untouched, and the footprints will last long after the last human has gone, silent witnesses to the fact that once, briefly, we were there. 1 million Earths could fit inside the sun. 1 million. If you hollowed out our star and started filling it with planet-sized marbles, you could pack in 1 million of them before you ran out of room, and yet by stellar standards the sun is unremarkable. Average. A middle-aged, a middleweight star, what astronomers call a G-type main sequence star, common enough that there are billions just like it scattered through the Milky Way. There are stars so much larger that they make the sun look like a pebble. Betelgeuse, for instance, a red supergiant in the constellation Orion, is so enormous that if you placed it where the sun is, its outer layers would extend past the orbit of Mars. Jupiter would be inside the star, so would we. Earth would orbit through Betelgeuse's atmosphere, skimming through its outer layers before being vaporized by heat measured in thousands of degrees. UY Scuti, one of the largest known stars, is even bigger. Its radius is roughly 1,700 times that of the Sun. If you started at its surface and travelled toward its centre at the speed of light, the fastest speed possible, it would take you several hours just to reach the core. These giants are rare, but they exist. bloated, dying stars in the final stages of their lives, burning through their fuel at reckless rates, shining with the light of hundreds of thousands of suns before they collapse and explode. Our sun will never become one of them. It's not massive enough. It will swell into a red giant, yes, but a modest one, large enough to swallow Mercury and Venus, perhaps Earth, but nothing like Betelgeuse. And then it will shed its outer layers and fade into a white dwarf, leaving behind a small, dense core that will cool slowly over trillions of years. Average, ordinary, and yet, to us, everything. The source of all the light and warmth that makes life possible, the anchor around which our world turns. Between Mars and Jupiter lies the asteroid belt, a region of space populated by millions of rocky bodies, remnants from the early solar system that never coalesced into a planet. When you hear asteroid belt, you might picture a dense field of tumbling rocks, a navigational hazard where spacecraft must weave and dodge to avoid collisions. But the reality is much emptier. The asteroid belt is vast. It stretches across tens of millions of miles, and while it contains millions of asteroids, those asteroids are spread so thinly that the average distance between them is hundreds of thousands of miles. If you stood on one asteroid and looked around, the next one would likely be too far away to see, even with a telescope, and are just a faint point of light, if that, lost among the stars. NASA has sent multiple spacecraft through the asteroid belt: Pioneer, Voyager, Cassini, New Horizons, and none of them have come close to hitting anything. The belt is so empty that mission planners barely think about it. They calculate trajectories to avoid known large asteroids, but mostly the spacecraft just coast through, surrounded by nothing but vacuum. It's a trick of perception. When we compress the solar system into diagrams and illustrations, we make the asteroids look close together because otherwise they'd be invisible dots on a mostly blank page. But space is big, bigger than we can easily visualize. Even regions we think of as crowded are, by earthly standards, almost perfectly empty. The asteroid belt isn't a field, it's a scattering. A handful of pebbles spread across a continent-sized room, each one drifting alone in the dark. Europa, one of Jupiter's moons, is a world of ice. Its surface is frozen solid, crisscrossed with cracks and ridges, gleaming white under the distant sun. But beneath that ice lies an ocean, a global ocean, liquid and dark, containing more water than all of Earth's oceans combined, more water than Earth, hidden beneath miles of ice, kept liquid by tidal heating as Jupiter's gravity kneads and flexes Europa's interior, generating warmth through friction. We've never seen this ocean directly. We've only inferred its existence from the way Europa's magnetic field interacts with Jupiter's, from the way the ice surface shows signs of movement and fracturing, from the plumes of water vapor that may be erupting from cracks in the ice, as venting into space like geysers. But if it's there, and most scientists believe it is, then Europa becomes one of the most intriguing places in the solar system. Because where there's liquid water, where there's energy, where there's chemistry happening in the dark, there's the possibility of life. Not intelligent life, probably not even complex life, but perhaps something simple. Microbes clustered around hydrothermal vents on the ocean floor, feeding on chemical energy the way life does in Earth's deepest oceans, in places where sunlight never reaches. It's speculative. Hopeful, maybe, but not impossible. And that's enough to make Europa worth visiting. Plans are already in motion. spacecraft designed to orbit the moon, to study its ice, to search for more evidence of the ocean beneath. Maybe someday we'll send a lander. Maybe we'll drill through the ice, lower a probe into the water and see what's there. Maybe we'll find we're not alone, even in our own solar system. Or maybe we'll find nothing but cold water and silence. Either way, we'll know. Titan, Saturn's largest moon, is the only moon in the solar system with a substantial atmosphere. Not a thin wisp of gas, not trace molecules clinging to the surface, but a thick, dense atmosphere, thicker than Earth's, pressing down with a pressure 1.5 times what we experience at sea level. And it rains on Titan. Not water rain. The surface temperature is minus 290 degrees Fahrenheit, far too cold for liquid water. Instead, Titan's rain is methane, liquid natural gas falling from hydrocarbon clouds, pattering onto a landscape of ice and organic sludge. There are lakes on Titan, rivers, seas, or even bodies of liquid methane and ethane pooling in basins, fed by rainfall and runoff, evaporating in the faint warmth of the distant sun and condensing again in the upper atmosphere. It's a hydrological cycle, just like Earth's, but with completely different chemistry. If you could stand on Titan's surface, protected from the cold, breathing your own air, you'd see a hazy orange sky, thick with smog. The sun would be a dim, pale disk, barely visible through the atmospheric murk. The landscape would be alien but strangely familiar. Rolling plains, river valleys, coastlines, dunes made of organic particles shaped by winds that blow at just a few miles per hour but move material easily in the low gravity and thick air. It's the most Earth-like place we've found, and yet nothing like Earth at all. A world where the familiar processes, weather, erosion, the cycle of evaporation and precipitation, play out in an environment so cold and strange that water is as hard as rock, and methane flows like water. We've landed there once. The Huygens probe descended through Titan's atmosphere in 2005, taking pictures, measuring temperatures and pressures, recording the sounds of an alien wind. It survived on the surface for about 90 minutes before its batteries died, sending back a handful of images: a rocky plain, rounded pebbles, a flat horizon beneath an orange sky, and then silence. But those 90 minutes were enough to confirm what we'd suspected. Titan is a world of weather and geology and chemistry, a place where things change and flow and transform, even in the frozen reaches of the outer solar system. Right now, as you listen to this, you're moving through space at over 500,000 miles per hour. You don't feel it, of course. You're sitting still or lying down, your body at rest relative to the ground. But the ground itself is moving. The Earth is rotating, carrying you along at roughly 1,000 miles per hour at the equator, and the Earth is orbiting the Sun at 67,000 miles per hour, a great looping path through the inner solar system. But the Sun isn't sitting still either. The Sun, along with the entire solar system, is moving through the Milky Way galaxy at 514,000 miles per hour. We're orbiting the galactic center, a supermassive black hole called Sagittarius, a star, located about 26,000 light-years away. It takes us 230 million years to complete one orbit, or one galactic year. The last time the solar system were in this part of the galaxy, dinosaurs hadn't evolved yet. Pangaea was still intact. Life on Earth was mostly underwater, and the continents were slowly drifting into configurations that wouldn't resemble the modern world for hundreds of millions of years. We've been around the galaxy only about 20 times since the Sun was born. 20 laps in 4.5 billion years, and each lap takes us through different neighbourhoods, different densities of stars and dust, different cosmic environments that may have subtle effects on the solar system, changes in comet bombardment rates, variations in cosmic ray exposure, influences we're only beginning to understand. You're travelling through the galaxy at speeds that make a bullet look stationary. You're adrift in a vast, slow current, carried along by gravity and momentum, orbiting a black hole you'll never see, moving through a cosmos that never stops. And yet, from your perspective, everything is still. At the centre of the Milky Way, hidden behind thick clouds of dust and gas, lies Sagittarius A star, a supermassive black hole with a mass of 4 million suns. 4 million suns, compressed into a region of space smaller than Mercury's orbit, a gravitational well so deep that nothing, not even light, can escape once it crosses the event horizon. We can't see the black hole itself. Black holes by definition don't emit light, but we can see the effects. Stars near the galactic centre orbit Sagittarius, a star at incredible speeds, some completing an orbit in just a few years. By watching those stars, tracking their positions over time, astronomers have been able to calculate the mass and location of the black hole with remarkable precision. In 2022, we finally captured an image, not of the black hole itself, but of the glowing ring of matter surrounding it, superheated gas spiralling inward, glowing with X-rays and radio waves before disappearing forever beyond the event horizon. The image shows a bright ring with a dark centre, the shadow of the black hole silhouetted against the light of its accretion disk. It's a portrait of something that shouldn't exist, according to our everyday intuition. A place where space-time curves so steeply that the normal rules break down, where time slows to a crawl, where the fabric of reality itself warps into configurations our minds struggle to comprehend. And it's not unique. Most galaxies, perhaps all large galaxies, have supermassive black holes at their centres, millions or billions of solar masses lurking in the hearts of stellar cities, shaping the orbits of stars, influencing the evolution of their host galaxies in ways we're still piecing together. Their gravitational anchors, cosmic engines, remnants of the early universe, or the accumulated result of countless smaller black holes merging over billions of years. We're not entirely sure how they formed, how they grew so large, but they're there, silent, invisible, patient, at the centre of almost everything. When a massive star runs out of fuel, it dies in a cataclysm called a supernova. The core collapses in less than a second, releasing more energy in that instant than the star emitted over its entire lifetime. The outer layers rebound, exploding outward at a significant fraction of the speed of light, and for a few weeks the dying star shines brighter than an entire galaxy, brighter than 100 billion stars, visible across millions or tens of millions of light years, a beacon in the cosmic dark, announcing the end of one kind of existence and the beginning of another. Because supernovas aren't just destruction, they're creation. Inside a massive star, nuclear fusion builds heavier and heavier elements, hydrogen into helium, helium into carbon and oxygen into neon, magnesium, silicon, iron. But fusion stops at iron. Iron doesn't release energy when fused, it absorbs it. So when the core becomes iron, the star's energy source shuts off. Without the outward pressure from fusion, gravity wins, and the collapse begins. In the supernova, in those brief moments of unimaginable temperature and pressure, heavier elements are forged, gold, platinum, uranium. All the elements heavier than iron owe their existence to supernovas created in the explosion and scattered into space, seeding the cosmos with the raw materials for planets and eventually life. The iron in your blood was made in a supernova. The calcium in your bones, the gold in any jewelry you might wear, the oxygen you breathe, all of it came from dying stars, expelled in violent explosions billions of years ago, drifting through space until gravity gathered it into a new solar system, a new planet, and eventually you. We are quite literally made of stardust, not poetically, not metaphorically. Actually physically made from the remnants of stars that exploded long before the sun was born. Every second, high-energy particles called cosmic rays pass through your body. Dozens of them, hundreds maybe. Protons and atomic nuclei accelerated to near-light speed by supernovas, by black holes, by processes we don't fully understand, travelling across the galaxy and slamming into Earth's atmosphere. Most of them break apart when they hit air molecules, creating showers of secondary particles, muons, electrons, photons, that rain down on the surface. Some of those particles pass through you without interacting at all, slipping between atoms as if you weren't there. Occasionally one collides with a molecule in your body, depositing a tiny bit of energy, causing a tiny bit of damage. Your cells repair most of it. Evolution has given us mechanisms to deal with low levels of radiation. DNA repair enzymes, error-checking systems, and cosmic rays are part of the background radiation that life on Earth has always experienced. But in space, without Earth's atmosphere to shield them, astronauts receive much higher doses. They report seeing flashes of light when cosmic rays pass through their eyes, brief sparks of illumination caused by particles interacting with the retina or optic nerve. Even with their eyes closed in complete darkness, they see these flashes, random and unpredictable, reminders that space is not empty, that it's filled with invisible radiation streaming through the void. It's a strange sensation, by all accounts. Unsettling at first, but you get used to it. You learn to ignore the flashes, the same way you learn to ignore the floaters in your vision, or the hum of machinery on the space station. Still, it's a reminder. Space is not passive. It's active, energetic, filled with particles and fields and forces we can't see or feel directly, but that are always there, always present, interacting with everything, including us. Turn on an old analog television, the kind with antennas, and tune it between stations. You'll see static, white and black pixels dancing across the screen, a random speckled pattern accompanied by a hissing sound. About 1% of that static is from the Big Bang. The cosmic microwave background, the afterglow of the universe's birth, fills all of space. It's faint, just a few degrees above absolute zero, but it's everywhere. A constant whisper of radiation left over from the moment the universe became transparent, about 380,000 years after the Big Bang. Before that, the universe was opaque, too hot, too dense. Photons couldn't travel freely because they kept scattering off electrons and protons, bouncing around in a thick fog of plasma. But as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen, and suddenly light could travel. That light has been travelling ever since, stretched by the expansion of the universe from visible and ultraviolet wavelengths into microwaves, cooled from thousands of degrees to just 2.7 Kelvin, but still present, still detectable, and your television can pick it up. Not very well. Most of the static is local interference, but a tiny fraction of those dancing pixels represents photons that have been travelling through space for over 13 billion years, bouncing off your antenna and into your screen. It's a connection to the distant past, a signal from the early universe, still echoing through the cosmos, faint but persistent, a reminder that we live in the aftermath of an event so vast and so long ago that we can barely imagine it, and yet its effects are still here, still measurable, still painting static on our screens. Galaxies come in different shapes, spirals with graceful arms, ellipticals that are smooth and featureless, irregulars that defy easy classification. Each shape tells a story of formation, evolution, and sometimes collision. Spiral galaxies like the Milky Way have a flat disk of stars rotating around a central bulge. The spiral arms aren't fixed structures, they're density waves, regions where stars and gas are temporarily compressed, triggering star formation and creating the bright, visible patterns we associate with spirals. Stars move in and out of the arms over time, but the arms themselves persist like waves on water. Elliptical galaxies are older, quieter. They've mostly used up their gas, so star formation has slowed or stopped. Their stars orbit in random directions, creating a smooth, three-dimensional distribution without the organized rotation of a spiral. Many ellipticals form through galactic mergers, two or more galaxies colliding and blending together, scrambling their orbits and erasing the delicate structures that spirals maintain. Irregular galaxies don't fit into either category. They're chaotic, often the result of gravitational interactions or recent mergers, still settling into a stable configuration, or they're small dwarf galaxies that never had enough mass to organize themselves into neat spirals or ellipticals. The Milky Way is a barred spiral, a spiral galaxy with a bar-shaped structure of stars running through its center. The bar funnels gas toward the core, feeding the central black hole and influencing star formation patterns throughout the galaxy. We didn't know we had a bar until relatively recently. It's hard to map the structure of your own galaxy when you're inside it, but observations of other stars' motions confirmed it. Every galaxy is a history book, written in the positions and velocities of its stars, and we're learning to read that history, to trace the story of how these vast cities of stars came to be. The Milky Way and Andromeda galaxies are heading toward each other at 250,000 miles per hour. In about 4.5 billion years they'll collide. It sounds violent, catastrophic. Two galaxies, each containing hundreds of billions of stars rushing together at 250,000 miles per hour. But galactic collisions aren't like car crashes. They're slow, stately dances that play out over hundreds of millions of years. The galaxies will pass through each other first. Stars are so far apart that actual stellar collisions will be vanishingly rare. Two stars hitting each other would be like 2 grains of sand colliding in a room the size of a city. Instead, the galaxies will interpenetrate, their gravitational fields pulling and tugging, distorting each other's shapes, flinging stars into new orbits. Then they'll separate, pull apart, turn around, and fall together again. And again. Each pass will mix them further, scramble their structures, until eventually they merge into a single larger galaxy, probably an elliptical. Since the collisions will disrupt the orderly spiral patterns both galaxies currently maintain. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda, a blending of the two names, fitting for a blending of two galactic cities. Earth will probably survive. The sun will probably survive. But the night sky will be unrecognizable. New constellations will form as stars shift positions. The Andromeda Galaxy, currently a faint smudge visible to the naked eye on dark nights, will loom enormous in the sky, growing larger and brighter as it approaches until it fills half the heavens, a great spiral stretched across the darkness before dissolving into chaos as the merger begins. Of course, by then the sun will be nearing the end of its life, swelling into a red giant, and Earth may already be uninhabitable. But if somehow we, or our descendants, or whoever comes after us are still around to witness it, the collision will be one of the most spectacular events in cosmic history. Two galaxies, meeting in the dark and becoming one. Dark matter makes up 85% of all matter in the universe. 85%, the overwhelming majority. And we have no idea what it is. We can't see it. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. It's invisible, not just hard to see, but fundamentally transparent to all the telescopes and instruments we've built. We know it exists only because of its gravitational effects. Galaxies rotate too fast. Their outer edges move at speeds that should fling them apart given the amount of visible matter they contain. Yes, something invisible is holding them together, providing extra mass, extra gravity. Galaxy clusters show the same effect. And when we look at the way light bends around massive objects, gravitational lensing, the amount of bending tells us there's far more mass present than we can account for with stars and gas and dust. So there's something out there. Dark matter. Kind of matter that interacts through gravity but seemingly nothing else. It forms halos around galaxies, vast spheres of invisible mass that extend far beyond the visible stars. It clumps and clusters on large scales, forming the cosmic web, the scaffolding around which visible matter organizes itself. But what is it? Theoretical particles called WIMPs, weakly interacting massive particles. Primordial black holes formed in the early universe. Something else entirely. Something we haven't even imagined yet. We've built detectors deep underground, shielded from cosmic rays, waiting for dark matter particles to pass through and interact with ordinary matter. So far, nothing conclusive. We've searched for it with particle accelerators. Still nothing. It's out there, surrounding us, passing through us maybe. 5 times more abundant than ordinary matter, and we're blind to it, groping in the dark, trying to understand something we can't see, can't touch, can barely even conceptualize. 85% of the matter in the universe, and it remains a mystery. The universe is expanding. We've known this since the 1920s, when Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. Space itself is stretching, carrying galaxies along with it. But in the late 1990s, astronomers discovered something unexpected. The expansion is accelerating. It should be slowing down. Gravity should be pulling everything back together, or at least putting the brakes on the expansion. But instead, the expansion is speeding up. Distant galaxies are receding faster and faster, as if something is pushing them, counteracting gravity, driving space to expand at an ever-increasing rate. We call this something dark energy, though the name is just a placeholder for our ignorance. We don't know what it is. We don't know where it comes from. We don't even know if it's a substance or a property of space itself. What we do know is that it makes up 68% of the universe. More than 2/3 of everything is this mysterious force or field or property, whatever it is, pushing the cosmos apart. Combined with dark matter, that means 95% of the universe is invisible to us. Ordinary matter, the stuff we're made of, the stuff stars and planets and galaxies are made of, accounts for just 5%. We are, in a very real sense, a minority component, a thin layer of visible foam on top of a vast ocean of darkness. And dark energy is winning. As the universe expands, matter spreads out and becomes less dense, so its gravitational pull weakens. But dark energy seems to remain constant or even grow stronger. Eventually, billions of years from now, the expansion will accelerate so much that galaxies beyond our local group will recede faster than light, disappearing beyond our cosmic horizon, forever out of reach. The universe will grow dark and empty and cold, and we'll be left alone in a small cluster of galaxies surrounded by nothing but the fading echo of the Big Bang. Unless, of course, we're wrong about dark energy. Unless it changes, behaves differently in the future, reverses itself somehow. We don't know. We can't know, not yet. For now, all we can do is watch the universe accelerate into the dark and wonder why. Time doesn't pass at the same rate everywhere. According to general relativity, time moves more slowly in stronger gravitational fields, a phenomenon called gravitational time dilation. It's not noticeable in everyday life. The difference between time at sea level and time on a mountaintop is measured in nanoseconds. But it's real, measurable, confirmed by atomic clocks precise enough to detect the tiny shifts. GPS satellites have to account for this when they orbit about 12,000 miles above Earth's surface, where gravity is weaker, so time passes slightly faster for them than it does for us on the ground. If the satellites didn't correct for this, GPS coordinates would drift by miles within a single day. The system works only because engineers program the satellites to adjust their internal clocks, compensating for the relativistic effects. Astronauts on the International Space Station experience time dilation too, though in the opposite direction. They're moving fast. Orbital velocity is over 17,000 miles per hour. And according to special relativity, time slows down for objects in motion relative to stationary observers. The effect is tiny, just a few milliseconds over the course of a mission, but it's measurable. If you could somehow survive near a black hole's event horizon, time dilation would become extreme. Time would slow to a crawl relative to someone far away. You might experience an hour while years or centuries passed for distant observers. If you fell in, crossing the event horizon, the outside universe would appear to speed up, stars aging and dying in fast forward as you descended toward the singularity. Time is not a constant. It's flexible, malleable, shaped by gravity and motion. The stronger the gravity, the slower the clock. The faster you move, the more time stretches. Einstein figured this out with mathematics, with thought experiments, with a deep intuition about the nature of space and time. And then we confirmed it, again and again, with experiments and observations. It's strange, counterintuitive, is incompatible with our everyday experience, but it's true. Time is relative, and that changes everything. The nearest star system to Earth, after the Sun, is Alpha Centauri, a triple star system located 4.37 light-years away. That means light, travelling at its maximum speed, takes 4.37 years to cover the distance. Light is fast, unimaginably fast by human standards. It could circle the Earth 7.5 times in 1 second. But the universe is big, and even light takes years to cross interstellar distances. If we wanted to send a spacecraft to Alpha Centauri using current technology, it would take tens of thousands of years. Voyager 1, the fastest human-made object to leave the solar system, is travelling at about 38,000 miles per hour. At that speed, it would take over 70,000 years to reach Alpha Centauri if it were headed in that direction, which it's not. There are proposals for faster missions. The Breakthrough Starshot initiative envisions tiny spacecraft propelled by powerful lasers accelerating to 20% the speed of light. At that speed, they could reach Alpha Centauri in about 20 years. But the technology doesn't exist yet, and even if it did, the probes would be so small they could carry only minimal instruments, and they couldn't slow down. They'd zip past the star system in a matter of hours, snapping pictures and beaming data back to Earth before continuing into the void. Still, it's something, a glimmer of possibility, a hint that maybe someday we could send something to another star and see what's there. For now, Alpha Centauri remains impossibly distant, a neighbour by cosmic standards, separated from us by a gulf so vast that crossing it seems more like science fiction than science. And yet, the light from Alpha Centauri reaches us. Every photon that strikes your eye left that star just over 4 years ago, travelling across the emptiness, carrying information about a distant sun. We can study it, analyse its spectrum, learn about its composition and temperature and motion. We may never touch it, but we can see it, and that's something. Voyager 1, launched in 1977, is now over 15 billion miles from Earth. It's in interstellar space, the region between stars, having crossed the boundary where the sun's influence fades and the galaxy's influence begins. It's the most distant human-made object, travelling at about 38,000 miles per hour, carrying with it a golden record. The record contains sounds and images from Earth, music, Bach, Beethoven, Chuck Berry, traditional songs from around the world, greetings in 55 languages, natural sounds, surf, wind, thunder, birdsong, images of people, landscapes, diagrams explaining our location in the galaxy, our biology, our mathematics. It's a message to anyone who might find it, a statement. We were here. This is what we were like. This is the world we came from. The chances of anyone actually finding it are vanishingly small. Space is vast, and Voyager 1 is tiny. It will take 40,000 years to pass within a light year or so of another star, and even then it will be travelling through empty space, dark and silent, invisible unless someone happens to be looking in exactly the right place at exactly the right time. But we sent it anyway, because maybe, just maybe, someone will find it. Maybe millions of years from now, a civilization we can't imagine will detect this small, ancient probe drifting through their star system. Maybe they'll bring it aboard, decode the record, listen to our music, see our faces. Maybe they'll wonder about us, who we were, whether we still exist, whether we ever made it off our home planet out into the galaxy, or whether we stayed behind and faded into history. The golden record is a time capsule, a message in a bottle, cast into an ocean so vast that it swallows all sense of scale. It may drift forever, unnoticed and alone, or it may, against all odds, be found. Either way, it's out there, a piece of humanity, travelling through the stars. Red dwarfs are the smallest, coolest, longest-lived stars in the universe. They burn their fuel so slowly, so efficiently, that they can shine for trillions of years, far longer than the current age of the universe, which is only 13.8 billion years old. Not a single red dwarf has ever died of old age. Not one. Every red dwarf that formed when the universe began is still burning, still fusing hydrogen into helium, still glowing with a faint, steady light. They'll outlast everything. The sun will swell into a red giant and then collapse into a white dwarf in about 5 billion years. Massive stars will explode as supernovas. Even the universe itself may undergo profound changes. Accelerating expansion, heat death, a big rip or a big crunch, depending on the behavior of dark energy. But red dwarfs will keep burning. Long after the last massive star has died, long after the Milky Way and Andromeda have merged, long after galaxies have drifted so far apart that they can't see each other anymore, red dwarfs will still be there, patiently fusing hydrogen, emitting their dim red glow into the growing darkness. Eventually, trillions of years from now, they'll run out of fuel. They'll cool and fade, becoming black dwarfs, cold, dark remnants, the final stage of stellar evolution. But we'll never see it happen. The universe is too young. Red dwarfs have barely begun their lives. In a sense, we live in the early morning of the universe, when stars are still being born, when galaxies still shine brightly, when the cosmos is vibrant and active. The long afternoon, the era of red dwarfs burning alone in the dark hasn't even started yet. And maybe that's fitting. We exist at a time when the universe is still interesting, still full of light and motion and change. We wouldn't want to be here for the ending, for the slow fade into cold and silence. Better to be here now in the beginning, when everything is still possible. White dwarfs are the dense remnants of stars like the sun, what's left after a star has shed its outer layers and exhausted its nuclear fuel. They're about the size of Earth, but with a mass comparable to the sun's. A teaspoon of white dwarf material would weigh about 15 tons. They don't generate energy through fusion anymore. They're just cooling, radiating away the residual heat left over from their active years. It's a slow process. White dwarfs cool over billions of years, fading gradually from white to yellow to red to eventually black. A black dwarf is a white dwarf that has cooled completely, no longer emitting any light. It's the final fate of most stars, a cold, dark cinder, drifting through space, invisible except for its gravitational influence. But here's the thing, black dwarfs don't exist yet. The universe isn't old enough. Even the oldest white dwarfs, formed shortly after the first stars ignited, are still glowing faintly. They haven't had time to cool completely. It will take trillions of years for a white dwarf to become a black dwarf. Trillions. By then, the universe will be unrecognizable. Galaxies dispersed, stars extinct. Only these cold remnants scattered through the void, monuments to a time when fusion lit the darkness. Our sun will become a white dwarf in about 5 billion years after it swells into a red giant and sheds its outer layers. It will glow for a while, tens of billions of years maybe, and then it will fade. Slowly, imperceptibly, it will cool, degree by degree, until it's just a ball of carbon and oxygen, frozen and dark, orbiting the galactic center in silence. And then, for the rest of time, however long that is, it will drift, a relic, a fossil. The sun as it was will be gone, but this remnant will persist, carrying with it the memory of the light that once warmed Earth. Some white dwarfs have cores made of crystallized carbon, diamond, essentially. Not the kind you'd find in a ring, This is carbon compressed under unimaginable pressure, cooled over billions of years, solidified into a crystalline lattice the size of a planet. As a white dwarf cools, the carbon and oxygen in its core eventually freezes, forming a solid crystal. The process starts at the center and works its way outward, like a pond freezing in winter. Eventually, the entire core crystallizes, leaving a giant cosmic diamond surrounded by a thin layer of lighter elements. In 2019, astronomers observed a white dwarf in the final stages of crystallization, its brightness pulsating in a way that suggested the core was solidifying. It's a confirmation of what theory predicted. White dwarfs crystallize as they age. Our sun will crystallize too eventually. Billions of years after it becomes a white dwarf, long after the Earth is gone, the sun's core will freeze into a diamond the size of a planet, spinning slowly through the dark. It's a strange kind of immortality. Not the blazing glory of a living star, but a quiet, enduring existence as a jewel in the void, beautiful in its way, and utterly, profoundly alone. Binary star systems, two stars orbiting each other, are more common than single stars like the Sun. About half of all stars in the Milky Way are part of binary or multiple star systems, locked together by gravity, circling a common center of mass. Some binaries are close, orbiting in hours or days. Others are widely separated, taking centuries to complete an orbit. And in some cases, planets orbit both stars, circumpolar planets or Tatooines, named after Luke Skywalker's homeworld in Star Wars. If you stood on such a planet, you'd see two suns in the sky. Two sources of light and warmth, rising and setting at different times, casting double shadows, recreating complex patterns of day and night depending on the planet's orbit and the stars' relative positions. It would be strange, beautiful maybe, but disorienting. Imagine trying to develop a calendar when your world is illuminated by two suns on different schedules. Imagine the myths and stories such a sky would inspire. Gods in pairs, dueling suns, eternal dances played out overhead. We've found planets like this. Kepler 16b, for instance, a gas giant orbiting two stars, one slightly smaller than the Sun, the other a red dwarf. The planet is cold, probably uninhabitable, but it exists, a real world with two suns, proof that systems we once thought belonged only to science fiction are scattered throughout the galaxy. And maybe some of those worlds are warm enough, stable enough, for life. Maybe somewhere, on a planet we haven't found yet, something looks up at a sky with two suns and wonders, just as we do, whether it's alone. There are planets that wander through the galaxy without stars, rogue planets, ejected from their home systems by gravitational interactions, drifting alone through the darkness. They were born the way all planets are born, coalescing from disks of gas and dust around young stars, but something went wrong. Maybe they strayed too close to a larger planet and got flung out by gravity's slingshot. Maybe their star went supernova and the explosion scattered its planets into the void. Or maybe they formed in chaotic systems where close encounters between planets were common and they simply lost the gravitational lottery. Now they drift. No sunrises, no sunsets, no seasons. Just eternal night, lit only by the faint glow of distant stars and the occasional cosmic ray. Any heat they retain comes from their formation, from radioactive decay in their cores, from the slow cooling of molten interiors, not from a star. We think there might be billions of these orphaned worlds in the Milky Way, maybe more rogue planets than stars. They're hard to detect, dark, cold, invisible except when they pass in front of a background star and their gravity bends the light, creating a brief brightening that lasts hours or days before they move on. Some might be gas giants like Jupiter. Others might be rocky, Earth-sized, with frozen surfaces and dead atmospheres. And some, just maybe, might still harbour warmth in their depths. Subsurface oceans heated by tidal forces or radioactive decay, protected from the cold of space by miles of ice. Places where, theoretically, life could exist, even in the absence of a sun. It's speculative, hopeful perhaps, but not impossible. These worlds are out there, wandering in the dark, remnants of systems long destroyed or scattered, carrying with them the silent history of their lost homes. And perhaps, on one of them, something endures, blind, isolated, but alive. The largest known structure in the universe is called the Hercules Corona Borealis Great Wall, a colossal supercluster of galaxies stretching across 10 billion light-years of space. 10 billion light-years. To put that in perspective, light from one side of this structure would take 10 billion years to reach the other side. That's longer than the time between the Big Bang and the formation of Earth. It's more than 2/3 the age of the universe itself. And it's not a solid object. It's a filament in the cosmic web, a concentration of galaxies bound together by gravity, tracing out the large-scale structure of the universe. From our perspective, it appears as a vast arc, a wall of light spanning an enormous portion of the sky, though of course we're seeing the galaxies as they were billions of years ago, their light only now reaching us after crossing cosmic distances. Structures this large challenge our understanding of how the universe formed. According to cosmological principles, matter should be distributed fairly uniformly on the larger scales. No structures bigger than a certain size. And yet, here's the Hercules Corona Borealis Great Wall, larger than theory predicted, a reminder that the universe still holds surprises, that our models are approximations, as incomplete sketches of a reality more complex than we've imagined. It's humbling. We think we understand the cosmos, its laws, its history, its structure. And then we find something like this, something so vast it strains the limits of what our theories allow, and we're reminded how much we still don't know. The universe is bigger than our equations, stranger than our assumptions, and we're still learning to see it clearly. Gravitational waves are ripples in the fabric of space-time itself, caused by violent cosmic events, black holes colliding, neutron stars merging, massive objects accelerating in ways that distort the geometry of space and time. When two black holes spiral into each other, their dance shakes the universe. Space-time stretches and compresses, sending out waves that propagate at the speed of light, carrying energy away from the collision. By the time those waves reach Earth, often from billions of light-years away, they're incredibly faint, stretching and squeezing space by less than the width of a proton. Less than a proton. An atom's nucleus is about 100,000 times smaller than the atom itself, and gravitational waves distort space by even less than that. Detecting them requires instruments of almost unimaginable precision. Laser interferometers with arms several kilometers long, sensitive enough to measure changes in distance smaller than anything we've ever measured before, and yet we've done it. In 2015, the LIGO detectors in the United States picked up the gravitational waves from two black holes merging 1.3 billion light-years away. The signal lasted only a fraction of a second, a brief chirp, as the black holes spiraled together and merged, releasing more energy and gravitational waves than all the stars in the observable universe emit as light in the same instant. Since then, we've detected dozens of these events: black hole mergers, neutron-star collisions, even hints of more exotic phenomena. Each detection tells us something new about the universe, about how black holes form, how often they collide, how massive they can be. And it's not just information, it's a new sense. For all of human history, we've explored the universe through light, visible light, infrared, radio waves, X-rays, all forms of electromagnetic radiation. But now we can hear the universe through gravity itself, through the vibrations of space-time, a completely different channel of information that reveals things light alone could never show us. It's as if we spent our entire existence watching a silent movie, and suddenly someone turned on the sound. The detection of gravitational waves opened a new era in astronomy. For the first time, we could observe the universe not through light, but through the geometry of space-time itself, a fundamentally different way of seeing. Electromagnetic radiation, light, radio waves, X-rays, interacts with matter. It scatters, gets absorbed, blocked by dust and gas. There are regions of space we can't see with light because something opaque is in the way. But gravitational waves pass through everything. They don't care about matter. They propagate through planets, stars, even black holes themselves. Carrying information from the event that created them without being altered or absorbed. This means we can see things with gravitational waves that are invisible to light. The interiors of supernovas, the moments before black holes merge, the earliest instance of the universe when it was too hot and dense for light to travel freely. And we can combine observations. When two neutron stars collided in 2017, we detected both gravitational waves and light, gamma rays, X-rays, visible light, radio waves. Multiple telescopes around the world observed the event, watching the explosion unfold across the electromagnetic spectrum, while LIGO and Virgo listened to the space-time vibrations. This is multi-messenger astronomy. Using different channels, gravity, light, maybe someday neutrinos or cosmic rays, to build a complete picture of cosmic events. The way you might use sight and sound together to understand a scene more fully than either sense alone could provide. It's still early. We've only just begun to explore this new way of observing, but already it's changing how we understand the universe, revealing secrets hidden from light-based telescopes, showing us the cosmos in a way we've never seen it before. And there's more to come. Better detectors. Space-based interferometers that can detect lower frequency waves from supermassive black hole mergers. New discoveries waiting in the data. New mysteries to solve. New questions we haven't even thought to ask yet. The universe is speaking to us in a new language, and we're learning to listen. Magnetars are neutron stars with magnetic fields 1 trillion times stronger than Earth's. 1 trillion times. If a magnetar existed halfway between Earth and the Moon, its magnetic field would be strong enough to erase every credit card on the planet, disrupt electronics, and interfere with the bioelectric patterns in your nervous system. At close range, the effects would be even stranger. The magnetic field would distort the electron clouds around atoms, making chemistry behave differently. Water might become less fluid. Light might polarize in unusual ways. The fundamental interactions that govern how matter works would be altered by the sheer strength of the field. Magnetars form when certain massive stars collapse into neutron stars, and their magnetic fields become amplified by the compression. The rotation and the churning of charged particles in the star's interior create a dynamo effect, generating fields so intense they reshape the star's surface, creating mountains and valleys held in place not by rigidity, but by magnetic tension. And they're violent. Magnetars occasionally experience star quakes. The crust shifts, releasing energy, and the magnetic field reconfigures itself explosively. These events produce bursts of X-rays and gamma rays bright enough to be detected across the galaxy. In 2004, a magnetar flare hit Earth's atmosphere, briefly ionizing it, causing instruments to overload. The magnetar was 50,000 light-years away. 50,000 light-years, and it still affected us. It's a reminder of how powerful these objects are, how extreme the universe can be in places. Magnetars push the boundaries of physics, creating conditions we can't replicate, can barely even model, and they exist, and are scattered through the galaxy, spinning and flaring, monuments to the strange and terrible beauty of collapsing stars. The Hubble Space Telescope has captured images of galaxies so distant that we see them as they were over 13 billion years ago, when the universe was less than 1 billion years old. 13 billion years. The light from these galaxies has been travelling through space for almost the entire age of the universe, crossing unimaginable distances, stretching and red-shifting as space itself expanded, until finally it reached Hubble's mirrors and was focused into images. These are ancient galaxies, young galaxies really. We're seeing them in their infancy, when the universe was still forming its first structures, when star formation was chaotic and intense, when galaxies were smaller, more irregular. These still in the process of assembling themselves through mergers and collisions. Some of these galaxies no longer exist, at least not in the form we see them. They've merged with others, evolved, grown into the massive ellipticals and spirals we see in the nearby universe, or they've been torn apart by tidal forces, their stars scattered, their gas stripped away. We're looking at fossils, snapshots of a time so long ago that the galaxies themselves might not remember it, encoded in light that has travelled across the cosmos to reach us. And there's more to see. The James Webb Space Telescope, launched in 2021, can see even farther, even deeper into the past. It detects infrared light, which means it can see through dust clouds that block Hubble's view, and it can spot galaxies so distant, so redshifted, that their visible light has been stretched into the infrared. We're pushing back the boundaries of the observable universe, reaching toward the moment when the first stars ignited, when darkness gave way to light for the first time, and maybe, eventually, we'll see all the way back, to the cosmic microwave background, to the afterglow of the Big Bang itself, the oldest light in existence. We're archaeologists of the cosmos, digging through layers of time, uncovering the history of everything. Exoplanets, planets orbiting stars other than the Sun, number in the thousands now, with new discoveries announced regularly. We've found gas giants larger than Jupiter, rocky worlds smaller than Earth, planets that orbit so close to their stars they're molten on one side, planets so far out they're frozen solid. Some orbit in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right potentially for life as we know it. We don't know if any of these worlds actually harbour life. We've found no definitive evidence, no biosignatures in their atmospheres, no signals from civilizations, nothing that unambiguously indicates biology. But the potential is there. Planets with the right temperature, the right size, maybe even water vapor in their atmospheres, oxygen, methane, gases that on Earth are produced by life. It's tantalizing, frustrating too, because we can't visit these worlds. They're light years away, far beyond the reach of our spacecraft. All we can do is observe from a distance, analysing the light that filters through their atmospheres, then looking for chemical clues that might hint at life. But even that is remarkable. A few decades ago, we didn't know if planets around other stars even existed. Now we know they're common. More planets than stars, probably, scattered throughout the galaxy. And some of them, maybe many of them, might be habitable. The question shifts from are there other Earths to how common are they? And the answer seems to be more common than we thought. Maybe not next door, but out there, somewhere, circling distant suns, waiting. Whether they're inhabited is another question entirely. HD 189733b is a planet about 63 light-years from Earth, a hot Jupiter, a gas giant orbiting close to its star, tidally locked so one side always faces the star while the other is in perpetual darkness. It's a world of extremes. Either the dayside reaches temperatures over 1,700 degrees Fahrenheit. The night side is cooler, but still scorching by any reasonable standard, and the temperature difference drives winds. Supersonic winds, screaming from the hot side to the cold side at speeds exceeding 5,400 miles per hour. But here's the strangest part. It rains glass. The atmosphere contains silicate particles, tiny fragments of vaporized minerals suspended in the heat. On the night side, where temperatures drop, these particles condense into glass, forming droplets that fall through the sky. But the winds are so fast, so violent, that the rain doesn't fall straight down. It flies sideways, horizontal sheets of molten glass tearing through the atmosphere at thousands of miles per hour. It's hard to even imagine. A sky filled with shards of glass, whipped by winds faster than the speed of sound, under a sun that never moves, baking one hemisphere while the other freezes in darkness. And it's real. Not speculation, not science fiction. A planet we've observed, whose properties we've measured, whose nightmarish weather we've mapped from 63 light-years away. The universe is stranger than we think. Stranger, maybe, than we can think. And HD 189733b is just one example. One data point in a galaxy full of worlds we're only beginning to discover. Some exoplanets are made almost entirely of water. Ocean worlds with no solid surface. Just water hundreds of miles deep, stretching from the atmosphere down to the core. Hundreds of miles. On Earth, the deepest parts of the ocean are about 7 miles down. Imagine an ocean 50 or 100 times deeper, pressing down with unimaginable weight, creating pressures so intense that water doesn't behave the way we expect. At great depths, under extreme pressure, water transforms. It doesn't freeze in the normal sense. Instead, it enters exotic states called hot ice, or superionic ice, where oxygen atoms lock into a crystalline lattice, while hydrogen atoms flow freely through it, creating a solid that conducts electricity like a metal. These ocean worlds might have layers, liquid water near the surface, exotic ices deeper down, and at the core perhaps rock or metal. Or maybe the entire interior is water in various strange phases, compressed and heated until it's nothing like the water we know. Could life exist in such an ocean? Maybe. On Earth, life thrives in deep-sea environments, near hydrothermal vents, and in places where sunlight never reaches. If an ocean world has enough internal heat, enough chemical energy circulating through its depths, then maybe something could live there, blind, adapted to pressure, to darkness, to an environment utterly alien to us. We don't know. We've found planets we think might be ocean worlds based on their size and density, but we can't see their surfaces, can't probe their depths. All we have are models, educated guesses, extrapolations from physics. But the possibility is there. Worlds made of water, drifting through the galaxy, silent and deep, perhaps harbouring life in their abyssal zones, in pressures and temperatures we can barely comprehend. The James Webb Space Telescope, launched in 2021, is the most powerful telescope ever built. It can detect the heat signature of a bumblebee at the distance of the moon, a tiny faint source of warmth against the cold of space, resolved with clarity that would have seemed impossible just a generation ago. This sensitivity allows it to see through cosmic dust clouds that block visible light, revealing the places where stars and planets are forming, hidden nurseries where gravity is slowly shaping gas and dust into new worlds. It can analyze the atmospheres of exoplanets, detecting the chemical fingerprints of molecules in the light that passes through or reflects off their atmospheres. Water vapor, carbon dioxide, methane, compounds that might indicate habitability or even life, and it can see farther back in time than Hubble, detecting galaxies from the early universe, then studying the first stars and galaxies that formed after the Big Bang, piecing together the history of cosmic dawn, the moment when darkness gave way to light. Already, it's found surprises, galaxies that seem more massive, more organized than expected at such early times, star formation happening in environments we thought were too hostile, structures and phenomena that challenge our models, that force us to rethink how the universe evolved. And it's just getting started. Webb is designed to operate for at least 10 years, possibly longer. Every observation adds to our understanding. Every image reveals something new, sometimes confirming what we suspected, sometimes upending what we thought we knew. It's a tool for exploration, a window into the universe's past and present, in a machine built to answer questions we've wondered about for generations and to raise new questions we haven't imagined yet. And somewhere, in the data streaming back from its orbit 1 million miles from Earth, there might be a discovery waiting, something that changes everything. Comets are ancient, icy remnants from the formation of the solar system, frozen leftovers that never became part of a planet, preserved in the cold outer reaches for billions of years. We call them dirty snowballs, though that's almost too gentle a description. They're mixtures of ice and rock and organic compounds, dark and pitted, spinning slowly through space until something, a gravitational nudge from a passing star, a disturbance in the Oort cloud, sends them tumbling inward toward the sun. As they approach, solar radiation begins to work on them. The ice sublimates, turning directly from solid to gas without melting first. Water vapor, carbon dioxide, dust particles, all of it streams away from the comet's nucleus, pushed by the solar wind and radiation pressure, forming a tail that can stretch millions of miles across space. 2 tails, actually. One made of dust following the comet's orbital path glowing with reflected sunlight. The other made of ionized gas always pointing away from the sun, blown by the solar wind like a flag streaming in a gale. And comets are beautiful. When a bright one passes close to Earth, it becomes visible to the naked eye, a fuzzy star with a tail, moving slowly against the background of fixed constellations, a visitor from the distant reaches of the solar system. ancient cultures saw them as omens, as harbingers of change or disaster. Oh, we know better now. They're not omens, they're messengers, carrying information about the early solar system, about the composition of the primordial cloud from which the sun and planets formed. Every comet is a time capsule, a sample of the ancient past delivered to the present. And they're fragile. Each pass near the sun strips away more material, more ice. Eventually they exhaust themselves, leaving behind only a rocky core or disintegrating entirely, scattering debris along their orbit that later becomes meteor showers when Earth passes through. Beautiful, brief, and ultimately doomed, like so much else in the cosmos. Beyond Neptune, far beyond Pluto, lies the Oort cloud, a vast spherical shell of icy objects surrounding the solar system, extending halfway to the nearest star. Halfway. The Oort cloud's outer edge may reach a light year from the sun, possibly more. It's so distant that sunlight takes months to reach it, so far out that the sun appears as just another bright star, no longer the dominant source of light and warmth, and it contains trillions of comets. We've never seen the Oort cloud directly. It's too far, too faint, the objects within it too small and dark to detect with current telescopes. But we infer its existence from the comets that occasionally fall inward, their orbits traced back to a source far beyond the known planets. These long-period comets come from the Oort cloud, nudged by passing stars, by gravitational perturbations, by the slow dance of the galaxy itself. They fall toward the sun on orbits that take thousands or millions of years to complete, appearing once in human history, putting on a brief show, and then vanishing back into the dark for millennia. The Oort cloud is the true edge of the solar system, the boundary where the sun's gravity fades and other stars begin to matter. It's a frontier we've barely explored, a region we know exists but have never touched, filled with ancient ice and rock, silent witnesses to the solar system's birth. And it's patient. The comets wait there, undisturbed, until something shifts their orbits and sends them falling inward, toward the light, toward warmth, toward us. Some stars travel so fast they can escape the Milky Way's gravity entirely. We call them hypervelocity stars, and they're moving at speeds exceeding 1,000,000 miles per hour, fast enough to break free from the galaxy and fly into intergalactic space. How do stars reach such speeds? Most of them are flung out by close encounters with Sagittarius A star, the supermassive black hole at the galaxy's center. A binary star system wanders too close. The black hole's gravity tears the pair apart, capturing one star and flinging the other outward at tremendous velocity. A gravitational slingshot on a cosmic scale. The ejected star rockets away, carrying with it the memory of its lost companion, travelling so fast it will eventually leave the galaxy entirely, crossing into the void between galaxies where almost nothing exists, just the faint hum of the cosmic microwave background and the distant, unreachable light of other galaxies. It's a lonely fate, to be ripped from your home, cast out into the darkness, travelling forever with no chance of return. The hypervelocity star will spend the rest of its life in exile, yet burning through its fuel alone, far from the galactic neighbourhood where it formed. We've found dozens of these runaway stars, and there are probably many more we haven't detected yet. Each one tells a story of violence, of close encounters with forces too powerful to resist, of being in the wrong place at the wrong time. The galaxy doesn't care. It continues its slow rotation, its stars orbiting the center in orderly patterns, while the hypervelocity stars flee into the void, refugees from gravitational chaos, speeding toward a future in the dark. The universe isn't distributed evenly. If you could step back and view it on the larger scales, you'd see structure. A cosmic web of galaxies arranged along filaments like threads in a vast three-dimensional tapestry, surrounding enormous voids where almost nothing exists. The filaments are where the matter is, where galaxies cluster together, drawn by gravity into dense regions. They stretch across hundreds of millions of light years, connecting galaxy clusters the way roads connect cities. And between the filaments, voids, vast empty regions underdense and dark, containing very few galaxies. Some voids are hundreds of millions of light years across, so large that if you were in the center of one, looking out in any direction, you'd see almost nothing, just darkness. A few faint distant galaxies at the edges, but mostly empty space, stretching on and on. This web-like pattern emerged from tiny quantum fluctuations in the early universe, random variations in density smaller than atoms that existed in the first moments after the Big Bang. As the universe expanded, those fluctuations grew. Denser regions attracted more matter. Less dense regions lost matter to their surroundings. Over billions of years, the pattern amplified, creating the cosmic web we see today. It's beautiful, in an abstract way. The structure of the universe, revealed not in individual stars or galaxies, but in the patterns they form when viewed as a whole, threads of light surrounding oceans of dark. And it's still evolving. Galaxies are still moving, still clustering along the filaments, still falling into the densest regions. The cosmic web is dynamic, shaped by gravity's slow but relentless pull, changing over timescales so long that we can barely perceive the motion. But it's there. The universe is not static. It's flowing, restructuring itself, weaving new patterns in the dark. Quasars are the brightest objects in the universe, so bright that a single quasar can outshine an entire galaxy of hundreds of billions of stars. They're powered by supermassive black holes at the centers of galaxies, feeding on enormous amounts of matter. Gas and dust spiral inward, forming an accretion disk that heats up as it falls, glowing with X-rays and visible light and radio waves, shining across billions of light years. When we look at quasars, we're seeing black holes in the act of feeding, actively consuming their surroundings, growing larger, releasing energy in the process. It's a violent, chaotic process. The accretion disk churns and flares. Jets of particles shoot out from the black hole's poles, travelling at near light speed, blasting through space for thousands of light years. And it's temporary. Our quasars don't last forever. Eventually the black hole exhausts the available fuel. The nearby gas and dust get consumed or blown away by the quasar's intense radiation. The accretion disk fades, the jets shut off, and the black hole goes quiet, dormant, waiting for new material to fall in. Most quasars we see are ancient, distant galaxies from the early universe, when supermassive black holes were still growing, still gorging themselves on the abundant gas available at that time. The nearby universe is quieter. Most black holes have already fed, already grown to their final masses, and now they sit dark and dormant at the centers of galaxies, including our own. But the Milky Way's black hole could become a quasar again, if enough matter fell into it. Maybe when Andromeda collides with us in a few billion years, the merger will funnel gas toward the center, reigniting the accretion disk, turning our quiet black hole into a blazing quasar visible across the cosmos. For now, though, it's silent, a giant sleeping in the dark. The most distant quasars are over 13 billion light-years away. Their light has been travelling toward us for most of the age of the universe, crossing unfathomable distances to reach our telescopes. We see them as they were when the universe was young, less than 1 billion years old, still in its infancy, still forming its first galaxies and structures. These ancient quasars tell us that supermassive black holes existed early, much earlier than we expected. Black holes with billions of solar masses, already feeding, already shining when the universe itself was barely out of its cradle. How did they grow so large? How so quickly? We're not entirely sure. Black holes grow by consuming matter, but there's a limit to how fast they can feed. The Eddington limit, where the radiation pressure from the accretion disk pushes away incoming matter, preventing further growth. At that rate, it should take much longer to build billion solar mass black holes. Maybe they started from heavier seeds, black holes that formed directly from collapsing gas clouds, rather than from dying stars. Or maybe they fed more efficiently than our models predict, growing faster through some process we don't fully understand. Either way, they're there. Ancient, distant, shining across the cosmos, reminders that the early universe was stranger, more active, more violent than we sometimes imagine. Not a quiet, empty place slowly assembling itself, but a furnace of star formation and black hole growth, galaxies colliding and merging, quasars blazing in the dark. And the light from those quasars is still travelling. Some of it is reaching us now, 13 billion years after it was emitted, carrying information about a time so distant, it feels almost mythological. The cosmic dawn, when light first pushed back against the darkness, and the universe began to resemble the place we see today. Gamma-ray bursts are the most powerful explosions in the universe since the Big Bang. For a few seconds, sometimes less, they release more energy than the sun will emit in its entire 10 billion year lifetime. More energy than the sun's entire life, in seconds. They come from the deaths of massive stars, or from collisions between neutron stars, events so violent that they momentarily outshine everything else in the sky, visible across half the observable universe. Most of the energy is released as gamma rays, high-energy photons that can't penetrate Earth's atmosphere, thankfully. We detect them with space-based telescopes, watching for the brief brilliant flashes that signal a gamma-ray burst somewhere in the cosmos, and they're directional. Gamma-ray bursts don't radiate energy equally in all directions. They focus it into narrow jets, beams of radiation fired along the rotation axis of the collapsing star or merging neutron stars. If the jet points toward Earth, we see a burst. If it points elsewhere, we might miss it entirely, seeing only the afterglow, the fading light from the explosion, just visible in X-rays and visible light and radio waves. If a gamma-ray burst occurred close to Earth, within a few thousand light-years, and pointed directly at us, it could be catastrophic. The gamma rays would strip away the ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. It might trigger a mass extinction, disrupting ecosystems, killing off species that can't adapt quickly enough to the changed environment. Fortunately, gamma-ray bursts are rare, and the nearby stars capable of producing them aren't oriented toward us. We're safe, at least for now. But somewhere in the universe right now a star is collapsing, or two neutron stars are spiraling together, and in a few moments they'll produce a gamma-ray burst, a brief blinding flash that will outshine galaxies, announcing to the cosmos that something has died in fire and light. The Pillars of Creation are one of the most iconic images in astronomy. Towering columns of gas and dust, photographed by the Hubble Space Telescope in 1995, backlit by the glow of nearby stars. They're located in the Eagle Nebula, about 7,000 light-years from Earth, and they're enormous. Each pillar stretches 4 to 5 light-years in height, about the distance from the Sun to the nearest star. If you could stand at the base of one and look up, the top would be trillions of miles away, lost in the haze of dust and starlight. These pillars are star nurseries. Inside them, gravity is slowly gathering matter together, compressing gas and dust into denser and denser knots until, eventually, fusion ignites and new stars are born. The process is slow, unfolding over millions of years, hidden from view by the thick clouds of material. But it's also destructive. The same massive stars that illuminate the pillars, making them visible, are also eroding them. Stellar winds and radiation eat away at the gas, sculpting the pillars, carving intricate shapes, and eventually the pillars will be gone, dispersed into space, their material scattered, leaving behind only the newborn stars they helped create. In fact, the pillars might already be gone. The light we see left the Eagle Nebula 7,000 years ago. If a nearby supernova went off 6,000 years ago, the shockwave could have already destroyed the pillars. We just wouldn't know yet. The light showing their destruction is still on its way, crossing the vast distance between us. For now, though, they endure, at least in our sky, in the images we capture, in the light that reaches us from the past. Beautiful, fragile temporary monuments to the process of creation, standing tall in the dark. Stars are born in nebulae, vast clouds of gas and dust that drift through the galaxy, sometimes spanning hundreds of light years, containing enough material to create thousands or even millions of stars. The process begins with gravity. A region of the nebula, slightly denser than its surroundings, starts to attract more material. The attraction grows stronger as more mass accumulates. The cloud begins to collapse, slowly at first, then faster, falling inward under its own weight. As it collapses, it heats up. Gravitational energy converts to thermal energy, warming the core. The temperature rises, thousands of degrees, then tens of thousands, then hundreds of thousands. And when it reaches about 10 million degrees, something remarkable happens. Fusion ignites. Hydrogen atoms, compressed and heated beyond imagining, overcome their mutual repulsion and fuse together, forming helium and releasing energy. The star begins to shine. The collapse halts, balanced by the outward pressure from fusion. A new star is born. It takes millions of years. From the first gravitational stirrings to the ignition of fusion, the process is slow, patient, inevitable. And it's happening right now, all over the galaxy. Stars being born in dark clouds, lighting up for the first time, joining the billions already shining. Our sun was born this way 4.5 billion years ago in a nebula long since dispersed. The cloud that gave birth to the solar system no longer exists, its gas scattered by stellar winds, and incorporated into other stars, blown into interstellar space. But the sun remains, still burning, still fusing hydrogen, a child of that ancient cloud. And in nebula scattered across the Milky Way, the process continues. New stars igniting, new lights appearing in the dark. When a star begins fusion, it doesn't burn like a fire. There's no combustion, no oxygen, no flame. Instead, It converts hydrogen into helium through nuclear reactions, a process governed by Einstein's equation E equals mc squared, turning a tiny amount of mass directly into energy. Tiny, but not insignificant. The mass difference between 4 hydrogen atoms and 1 helium atom is only about 0.7%. But 0.7% of the mass converted to energy is enormous. The Sun converts 4 million tons of matter into pure energy every single second. 4 million tons simply ceasing to exist as matter and becoming light and heat instead. And it's been doing this for 4.6 billion years. Despite losing 4 million tons per second, the Sun has barely changed. It still has enough hydrogen to continue fusing for another 5 billion years or so. The fuel supply is so vast and the conversion so efficient that even burning at this prodigious rate, the Sun will shine for 10 billion years total before it runs out. This is the heart of a star, a fusion reactor, balanced on the edge between gravitational collapse and explosive expansion, held in equilibrium by the delicate interplay of forces. Too much pressure and the star would explode. Too little and it would collapse. But in the narrow band where the forces balance, fusion continues stable and steady, converting hydrogen to helium, mass to energy, darkness to light. It's alchemy, in a sense. Not the medieval dream of turning lead into gold, but something far more profound. Turning mass into energy, turning the simplest element into something more complex. Building the universe, atom by atom, photon by photon, in the cores of stars scattered across the cosmos. Brown dwarfs are sometimes called failed stars, objects too massive to be planets, but too small to sustain hydrogen fusion in their cores. They fall into a gap between the two categories, neither one nor the other, drifting through space in a kind of cosmic limbo. They form the same way stars do, collapsing from clouds of gas and dust gathering mass through gravity. But they never quite reach the critical threshold. A star needs about 80 times Jupiter's mass to ignite hydrogen fusion. Brown dwarfs have less than that, anywhere from 13 to 80 Jupiter masses, enough to compress their cores and heat them, but not enough to sustain the fusion reactions that power true stars. Some of them can fuse deuterium, a heavier isotope of hydrogen, for a brief time. But deuterium is rare, and the fusion doesn't last long. Eventually the fuel runs out, and the brown dwarf is left with nothing but the heat of its formation, slowly radiating it away into space. They glow, faintly. Not with the light of fusion, but with leftover warmth, infrared radiation, invisible to the human eye but detectable with specialized telescopes. Over billions of years they cool, dimming gradually, fading from red to brown to eventually theoretically black, though the universe isn't old enough yet for any brown dwarf to have cooled completely. They're common, we think, possibly as numerous as stars scattered throughout the galaxy, hard to detect because they're so dim. Silent, cooling embers, neither planet nor star occupying a category of their own. And they're patient. They don't burn out like stars, they just cool, slowly, inevitably, over timescales so long that their story is still being written, billions of years in, with trillions more to go. The universe has no center. It's one of the strangest things about the Big Bang. There's no point in space you can identify as the origin, no location where the explosion happened. Because it wasn't an explosion into space, it was an expansion of space itself. Imagine the universe as the surface of a balloon and galaxies as dots on that surface. As you inflate the balloon, the surface stretches, and every dot moves away from every other dot. But there's no center on the surface, no dot that's more central than the others. Every point is equivalent. Every galaxy sees the same thing, everything else moving away, the farther objects receding faster. That's the universe. Three-dimensional space expanding, carrying galaxies along with it, with no center, no edge, no outside that we can point to or measure. The Big Bang happened everywhere at once. Every point in space was once compressed into the initial singularity, and every point participated equally in the expansion. There's no privileged location, no spot you can travel to and say, this is where it all started. It started here and there, and everywhere else simultaneously. It's counterintuitive. We're used to explosions having centers, to things expanding outward from a single point. But the Big Bang wasn't like that. It is something stranger, something that requires letting go of our everyday intuitions and accepting a universe that operates on principles we didn't evolve to understand. And yet we can understand it, with effort, with mathematics, with careful observation, with models that match what we see when we look out at the cosmos. The universe has no center, and that's not a failure of understanding. It's a feature, a deep truth about the nature of space and time. The cosmic microwave background has a temperature of 2.7 Kelvin, about minus 454 degrees Fahrenheit, just 2.7 degrees above absolute zero. This is the cooled remnant of the intense heat that filled the universe shortly after the Big Bang. Back then, the universe was a searingly hot plasma, thousands of degrees, opaque to light, glowing with the energy of its birth. As it expanded, it cooled. The temperature dropped degree by degree as space stretched and the energy spread out over a larger and larger volume. Eventually it cooled enough for electrons and protons to combine into neutral hydrogen atoms. The universe became transparent. Light could travel freely for the first time. That light has been travelling ever since, stretched by the expansion of the universe from visible wavelengths into microwaves, cooled from thousands of degrees to just a few degrees above absolute zero. But it's still here, filling all of space, a faint glow that surrounds us on all sides. We can detect it with radio telescopes mapping its temperature across the sky, and what we find is remarkable. It's almost perfectly uniform, almost the same temperature in every direction, varying by only about 1 part in 100,000. But those tiny variations matter. They represent density fluctuations in the early universe, regions that were slightly hotter or cooler, slightly denser or less dense. And those fluctuations, amplified by gravity over billions of years, became the cosmic web, the galaxies, the stars, the planets. Everything we see, everything that exists traces back to those tiny ripples in the cosmic microwave background, the seeds of structure encoded in the afterglow of the Big Bang, preserved for us to measure and study and wonder at. For the first 380,000 years after the Big Bang, the universe was opaque. Light couldn't travel freely through space because it kept scattering off free electrons, bouncing around like photons in a thick fog. Imagine trying to see through a cloud so dense that every photon you emit immediately hits something and scatters in a random direction. That was the early universe, a glowing plasma, hot and bright, but impossible to see through, even if there had been eyes to see. Then, as the universe expanded and cooled, something changed. the temperature dropped below the threshold where electrons and protons could combine into neutral hydrogen atoms. Suddenly there were no more free electrons to scatter light. The fog cleared. The universe became transparent. This moment is called recombination, though it's a bit of a misnomer. It's not that electrons were recombining with protons, since they'd never been combined before, but the name stuck. And the light that was released at that moment, the first light that could travel freely, is the cosmic microwave background we detect today. It's a snapshot of the universe at 380,000 years old, the earliest direct image we have of the cosmos. Before that, we can't see. The universe was opaque, and no light from earlier times has survived. We can infer what happened using physics and mathematics and observations of the cosmic microwave background structure. But we can't observe it directly. It's a horizon, in a sense, a boundary beyond which our telescopes can't reach, not because the light hasn't had time to get here, but because the light didn't exist yet, or couldn't travel. The universe's first 380,000 years are hidden from us, are locked behind the fog of the early plasma, and maybe they always will be. The observable universe has a diameter of about 93 billion light-years, even though the universe is only 13.8 billion years old. At first, this seems impossible. If the universe is 13.8 billion years old, shouldn't the most distant objects we can see be 13.8 billion light-years away? How can the observable universe be larger than the distance light has had time to travel? The answer is expansion. Space itself has been stretching while light travelled through it. A galaxy that emitted light 13 billion years ago was much closer to us back then, maybe only a few billion light-years away. But as its light travelled toward us, space expanded, carrying the galaxy farther away. By the time the light reaches us, the galaxy is much more distant than it was when the light was emitted. So we see the galaxy as it was 13 billion years ago, but the galaxy itself is now about 46 billion light-years away. And the same is true in every direction. The radius of the observable universe is about 46 billion light-years, making the diameter roughly 93 billion light-years. And it's growing. Every day, light from more distant regions reaches us for the first time, expanding the boundary of the observable universe. Not because the universe itself is getting bigger, though it is, but because light has had more time to travel, revealing regions that were previously too far for their light to have reached us yet. There are places we will never see, no matter how long we wait, are regions so distant that the expansion of space carries them away faster than light can travel toward us. Their light will never reach us. They exist beyond our cosmic horizon, forever out of reach, invisible, and unknowable. The universe is larger than we can observe, probably much larger, maybe infinite, but we'll only ever see a finite portion, bounded by the speed of light and the age of the universe. Planetary nebulae have nothing to do with planets. They were named by early astronomers who looked at them through primitive telescopes and thought they resembled planets. Round, glowing, disc-like. But they're not planets. They're shells of gas expelled by dying stars. When a sun-like star exhausts the hydrogen in its core, it begins to fuse helium into carbon and oxygen. This process is less stable, more chaotic, and eventually the star swells into a red giant, its outer layers expanding while its core contracts. At some point, the star sheds those outer layers. They drift away, pushed by stellar winds and radiation pressure, forming a glowing shell around the remaining core. The core itself becomes a white dwarf, hot, dense, radiating ultraviolet light that ionizes the expelled gas, making it glow in beautiful colours. That glowing shell is a planetary nebula. It lasts only a few tens of thousands of years before dispersing into interstellar space, recycling the star's material back into the galaxy, where it might eventually become part of new stars, new planets, new life. The Ring Nebula in Lyra is one of the most famous examples. So is the Helix Nebula, sometimes called the Eye of God because of its appearance, a circular shell of gas, glowing red and blue, with a white dwarf at the centre, staring out into space like a cosmic eye. And it's a preview. In about 5 billion years the Sun will do this. It will swell into a red giant, possibly swallowing Mercury and Venus, maybe even Earth. Then it will shed its outer layers, creating its own planetary nebula, a brief, beautiful display before it fades into a white dwarf, leaving behind a cooling ember where a vibrant star once burned. Globular clusters are ancient spherical collections of stars, some containing hundreds of thousands or even millions of stars, packed tightly together in a relatively small volume. They orbit galaxies like satellites, relics from the early universe, holding clues to the formation and evolution of galaxies themselves. The stars in globular clusters are old, very old, and some clusters are over 12 billion years old, formed when the universe was young, before the Milky Way took its current shape. Their stars are mostly red and yellow, cool, dim, long-lived stars that have been burning for eons. There are almost no blue, massive stars in globular clusters, because those stars burn out quickly, and any that existed when the cluster formed have long since died. And the stars are close. In the centre of a globular cluster, stars might be separated by only light days or light weeks, compared to the light years between stars in the galactic disk. If you lived on a planet in a globular cluster, your night sky would be spectacular. Thousands of stars bright enough to cast shadows, the sky never truly dark, just filled with points of light in every direction. But it would also be dangerous. Close stellar encounters would be more common. Gravitational interactions might perturb planetary orbits, ejecting planets from their systems or sending them crashing into their stars. The radiation environment might be harsher, with more supernovas and stellar flares in close proximity. Still, it's tempting to imagine a sky filled with stars, so many that constellations would be meaningless, navigation impossible without instruments. A night that's never fully night, just a dimmer version of day, lit by the combined glow of 1 million suns. Globular clusters orbit the Milky Way in halos, scattered above and below the galactic plane. We've catalogued about 150 of them, though there may be more hidden behind dust clouds or on the far side of the galaxy. Each one is a fossil, a remnant of the galaxy's youth, slowly orbiting, slowly evaporating as stars escape its gravity, but enduring for now as monuments to a time long past. The speed of light in a vacuum, 186,282 miles per second, is the universe's ultimate speed limit. Nothing with mass can reach it. Nothing can exceed it. It's a fundamental constant, woven into the fabric of space-time itself. Why? It comes down to relativity. As an object with mass accelerates, its energy increases. But according to Einstein's equations, as it approaches the speed of light, its effective mass increases too. requiring more and more energy to accelerate it further. To actually reach the speed of light would require infinite energy, which is impossible. So light speed is a barrier. Photons can travel at that speed because they have no mass. Anything with mass can only approach it, getting closer and closer but never quite reaching it. And there are consequences: time dilation, length contraction, the relativity of simultaneity. All of these emerge from the fact that the speed of light is constant in all reference frames, regardless of how you're moving. It's strange, counterintuitive. If you're on a train moving at 50 miles per hour and you throw a ball forward at 10 miles per hour, someone on the ground sees the ball moving at 60 miles per hour. The speeds add. But light doesn't work that way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, someone outside the ship still sees that light travelling at the speed of light, not 1.5 times the speed of light. The speeds don't add because time and space adjust to keep the speed of light constant. Time slows down for the moving observer, distances contract. The universe reshapes itself to preserve this one fundamental speed, and that limit defines what we can do, where we can go, how we can explore. The stars are separated by light years. At the speed of light, it would still take years to reach them. At any slower speed, which is the only speed we can achieve, it takes decades, centuries, millennia. The universe is vast, and the speed limit is unforgiving. We can dream of faster than light travel, but physics, as we understand it, says no. The speed of light is the speed of causality, the speed at which information and influence propagate through the cosmos, and we're bound by it, as is everything else. According to relativity, as you approach light speed, time slows down for you relative to stationary observers. This is called time dilation, and it's not a trick or an illusion. It's a real measurable effect. If you could travel at 99% the speed of light, time would pass about 7 times slower for you than for someone on Earth. A year on your ship would correspond to 7 years on Earth. Travel at 99.9% the speed of light, and the factor becomes about 22. A year for you, 22 years for everyone else. At speeds close enough to light speed, the effect becomes extreme. You could travel across the galaxy, 100,000 light years, and experience only decades or even years of time, while 100,000 years passed for the rest of the universe. It's a one-way trip in a sense. You could leave Earth, travel to a distant star and return, having aged only a few years. But when you got back, these centuries or millennia would have passed. Everyone you knew would be gone. Civilizations might have risen and fallen. The world you left would be unrecognizable. This is the twin paradox, though it's not really a paradox, just a consequence of relativity. One twin stays on Earth, the other travels at near light speed to a distant star and back. When they reunite, the travelling twin is younger, sometimes much younger, having experienced less time due to time dilation. It's been confirmed experimentally. Atomic clocks on fast-moving aircraft run slower than stationary clocks. GPS satellites have to account for time dilation, both from their speed and from the weaker gravity at their altitude, to maintain accuracy. Time is not absolute. It's flexible, shaped by motion and gravity. And if we ever achieve near light speed travel, we'll have to reckon with the consequences. The temporal disconnection, the isolation, the strange trade-off where you can travel vast distances in your own lifetime, but only by leaving your time behind. Wormholes are theoretical tunnels through space-time that could in principle connect distant parts of the universe. A shortcut, essentially. A way to travel between 2 points without crossing the space in between. Einstein's equations allow for them. General relativity doesn't forbid wormholes, but there are problems. First, they're probably unstable. A wormhole, if it formed naturally, would likely collapse almost immediately, pinching off before anything could pass through. To keep one open, you'd need exotic matter. Matter with negative energy density. Something we've never observed and aren't sure can exist in the quantities required. Then second, even if you could stabilize a wormhole, it's not clear you could use it for faster than light travel. Some solutions suggest that travelling through a wormhole would still take time, possibly as much time as it would take light to travel the conventional route. The wormhole would be a shortcut through space, but not through time. And third, there are causality issues. If wormholes could be used for faster than light travel, they might also allow time travel, looping back to the past, creating paradoxes. Some physicists argue that the universe has mechanisms to prevent this, that causality violations are impossible even in principle. Others aren't so sure. We've never found a wormhole. We've never seen evidence that they exist naturally. And creating one artificially would require technology and energy far beyond anything we can currently imagine. But they're not forbidden by the laws of physics, at least not the laws as we understand them, and that's tantalizing. Maybe, someday we'll understand space-time well enough to manipulate it, to create passages through it, to use the universe's own geometry as a highway. Or maybe wormholes are just mathematical curiosities, solutions to equations that describe things that can't actually exist in reality. For now, they remain theoretical, portals in the imagination, waiting to be proven possible or impossible. The Fermi paradox asks a simple question. If the universe is so vast and old, with billions of potentially habitable planets, where is everyone? The numbers seem to suggest we shouldn't be alone. The Milky Way contains hundreds of billions of stars. Many of them have planets. Many of those planets orbit in the habitable zone. Even if only a tiny fraction develop life, and only a tiny fraction of those develop intelligent life, and only a tiny fraction of those develop technology and the ability to communicate across space, even with all those filters, there should be thousands or millions of civilizations in our galaxy alone. And yet, we've detected nothing. No radio signals, no megastructures, no signs of engineering on galactic scales, no visits, no messages, no evidence that anyone else is out there looking back at us. Silence. Maybe life is rarer than we think. Maybe the jump from simple single-celled organisms to complex multicellular life is incredibly difficult, and Earth got lucky. Maybe intelligence is rare. Yeah, maybe technological civilizations destroy themselves before they can spread across the stars. Maybe interstellar travel is harder than we imagine, and civilizations stay confined to their home systems, never venturing out. Or maybe they're there, but we're not looking in the right way. Maybe they communicate using methods we haven't discovered yet. Maybe they're deliberately quiet, hiding, avoiding detection for reasons we can't fathom. Or maybe they simply don't care about us. We're too primitive, too distant, too uninteresting to warrant contact. The Fermi paradox isn't really a paradox. It's a question, an uncertainty, a gap between expectation and observation. And the answer, whatever it is, will tell us something profound about our place in the universe. Are we alone? Or are we just early, or isolated, or unnoticed? We don't know yet, but we're listening, searching, hoping that someday the silence will break. The Drake equation is an attempt to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. It's not a precise calculation, most of the variables are guesses, but it's a useful framework for thinking about the question. The equation multiplies several factors: the rate of star formation in the galaxy, the fraction of stars with planets, the number of planets per star that could support life, the fraction where life actually develops, the fraction where intelligent life emerges, the fraction that develop technology capable of communication, and the length of time those civilizations remain active and detectable. Plug in optimistic numbers and you get thousands or millions of civilizations. Plug in pessimistic numbers and you get one, us, or zero if you assume civilizations inevitably destroy themselves before they can communicate. The problem is that we only have one data point, Earth. We know life can arise, intelligence can evolve, technology can develop, but we don't know how common these steps are. We don't know if they're likely or vanishingly rare. And the final term, the lifetime of a civilization, is especially uncertain. How long do technological civilizations last? 100 years? 1,000? 1,000,000? We've only been capable of radio communication for about a century. Will we last another century? Another 1,000 years? Or will we collapse, destroy ourselves, fade into obscurity before we ever make contact? The Drake equation doesn't give us answers. It gives us questions. It reminds us how much we don't know, how many uncertainties remain, and it frames the search for extraterrestrial intelligence not as a simple yes or no question, but as a complex problem with many variables, many possible outcomes, and no easy solutions. We're searching, but we're searching blind, with no guarantee we'll find anything. The Great Filter hypothesis suggests there's a barrier, a step in the evolution from lifeless matter to spacefaring civilization that's extraordinarily difficult to pass, something that stops most potential civilizations from reaching the stars. If the filter is behind us, if the hard steps are in our past, then we're lucky. We've already passed the difficult stages, and the path ahead is relatively clear. Maybe the jump from non-life to life is incredibly rare. Maybe multicellular life is a fluke. Maybe intelligence almost never evolves. If so, we're rare, possibly unique, and we have a future ahead of us. But if the filter is ahead of us, the implications are darker. Maybe civilizations destroy themselves with nuclear weapons, or environmental collapse, or engineered pandemics. Maybe artificial intelligence turns against its creators. Maybe interstellar travel is impossible, or so difficult that no civilization ever achieves it. If the filter is ahead, then we're doomed, statistically speaking, destined to hit the same barrier that stopped everyone else. The unsettling question is, which is it? Are we the lucky ones who made it through, or are we just another civilization on the path to inevitable failure? We don't know. The universe gives us no clear answer. The silence could mean we're rare, or it could mean the filter is ahead, waiting, and we haven't reached it yet. Some people find the Great Filter depressing, but there's another way to look at it. If we can identify the filter, if we can understand the risks, then maybe we can avoid them. Maybe we can be the first to make it through, to prove that the filter isn't insurmountable, to become the civilization that survives. It's a challenge, a warning, and maybe, if we're careful, an opportunity. Panspermia is the idea that life might spread between planets, or even between star systems via meteorites, comets, or dust grains carrying microorganisms through space. It sounds far-fetched, but it's not impossible. Some microorganisms can survive in space, radiation-resistant bacteria, extremophils that can endure vacuum and cold. If a meteorite impact on a life-bearing planet ejects material into space, and some of that material contains microbes, those microbes could, in theory, drift through the solar system and land on another planet. We know material is exchanged between planets. Meteorites from Mars have been found on Earth, ejected by impacts on Mars and captured by Earth's gravity millions of years later. If Mars ever had life, if it has life now hidden in subsurface water or ice, then it's conceivable that Martian microbes have reached Earth, or that Earth microbes have reached Mars. On interstellar scales, it becomes more speculative. Could life spread between star systems? Maybe, if microbes can survive the journey, thousands or millions of years adrift in the void, frozen, dormant, waiting for gravity to capture them and deliver them to a new world. It's a romantic idea in a way. Life as a cosmic seed scattered across the galaxy by chance, taking root wherever conditions allow. Earth's biosphere might have started with a microbe that travelled from another world, or Earth might have seeded other planets, spreading life beyond its origin. We don't know if panspermia has happened. We don't even know if it's likely. But it's possible, and that's enough to make us wonder. If we find life on Mars, or Europa, or Enceladus, the first question will be, is it related to Earth life? Did it originate independently, or did we share a common ancestor delivered by a meteorite billions of years ago? The answer will tell us something important. Not just about life in the solar system, but about life in the universe, whether it's confined to single worlds, or whether it spreads, travels, connects distant planets in ways we're only beginning to imagine. The WOW signal, and detected in 1977 by the Big Ear radio telescope, remains the most intriguing potential message from an extraterrestrial civilization we've ever received. It was strong, very strong. A narrowband radio signal precisely at the frequency where hydrogen emits radiation, exactly the kind of frequency SETI researchers thought an alien civilization might use to get our attention. The signal lasted 72 seconds, the maximum time the telescope could observe it before Earth's rotation carried the source out of view. The astronomer who found it, reviewing the data printout days later, was so struck by the signal's characteristics that he wrote "Wow" in the margin. The name stuck. But the signal never repeated. Follow-up observations found nothing. The Big Ear telescope and later other telescopes had listened to the same region of sky at the same frequency and heard only silence. Whatever produced the WOW signal, if it was real, if it wasn't some artifact or interference, it spoke once and then went quiet. We don't know what it was. Natural phenomena can produce radio bursts, though none that perfectly match the WOW signal's profile. It could have been a fluke, a one-time event, something we don't have a good explanation for, but that doesn't require invoking aliens. Or it could have been a message, a deliberate transmission, or an accidental leak from some distant technology, crossing the galaxy and briefly intersecting with our telescope before moving on. We'll probably never know. The signal is gone, its source unknown, its meaning, if it had meaning, lost. But it remains a reminder that the universe might be trying to talk to us, and we might not always be listening at the right time in the right place to hear. Tabby Star officially known as KIC 846285, is a star about 1,300 light-years away that showed strange irregular dimming when observed by the Kepler Space Telescope. Most stars dim periodically if they have planets, transits, where a planet passes in front of the star and blocks a small fraction of its light. But the dimming is predictable, regular, and usually blocks only a % or so of the star's light. Tabby's star dimmed irregularly, sometimes by over 20%, with no apparent pattern. The dips were asymmetric, lasting different lengths of time, occurring at unpredictable intervals. Whatever was blocking the light, it wasn't a planet. One hypothesis: a swarm of comets are broken apart by a close encounter with another star or planet, creating a cloud of debris that passed in front of Tabby's star and caused the dimming. Another hypothesis, more speculative: a megastructure, a Dyson swarm perhaps, orbiting solar panels or habitats built by an advanced civilization, capturing the star's energy. The irregular dimming could be construction activity, pieces being added or moved, creating unpredictable occultations. It was a tantalizing idea, a potential techno-signature, evidence of alien engineering on scales we can barely imagine. But the truth is probably less exotic. Follow-up observations suggested the dimming is wavelength dependent. Bluer light dims more than red light, which is consistent with dust or debris, not solid structures. The most likely explanation is a natural phenomenon: dust clouds, possibly from comets or a disintegrated planet, orbiting the star and occasionally blocking our view, but we're not completely sure. The mystery isn't entirely solved. Tabby's star remains unusual, a reminder that the universe holds phenomena we don't fully understand, and that sometimes the simplest explanation isn't immediately obvious. Still, it was exciting briefly to imagine we'd found something built by someone else. A structure in space, a sign of intelligence, a neighbour reaching out across the stars. Maybe someday we will. But probably not at Tabby's star. The anthropic principle suggests that the universe appears fine-tuned for life because we wouldn't be here to observe it if it weren't. It's a selection effect. We exist in a universe where the physical constants allow for stars, planets, chemistry, and life, because those are the only universes where observers can arise. If gravity were slightly stronger or weaker, stars wouldn't form the way they do. If the strong nuclear force were different, atoms wouldn't be stable. If the cosmological constant, dark energy, were much larger, the universe would have expanded too quickly for galaxies to form. The range of values that permit life is narrow. Change any of several fundamental constants by even a small amount, and the universe becomes sterile. No stars, no planets, no chemistry complex enough for life. Some people see this as evidence of design, a universe deliberately constructed to produce life. Others see it as a brute fact, a coincidence we're lucky to benefit from. The anthropic principle offers a different interpretation. Maybe there are many universes, a vast multiverse, each with different physical constants. In most of them, nothing interesting happens, but in a few, the constants are just right, and observers evolve. We find ourselves in one of those universes not because it's special, but because that's the only kind of universe where we could exist to ask the question. It's a strange kind of explanation, not a mechanism, not a cause, just an observation about selection bias. We see a universe compatible with life because incompatible universes don't have anyone to notice them. Some physicists find this unsatisfying, others think it's profound. Either way, it's a reminder that the universe, our universe at least, is remarkably well suited to produce complexity, structure, and eventually us. Whether that's luck, design, or an inevitable consequence of a larger multiverse, we don't know. But we're here, or wondering about it, which is something. Some physicists propose that our universe is just one of countless universes in a vast multiverse, each with different physical laws, different constants, different properties. In some universes, gravity is stronger. In others, electromagnetism dominates. Some universes might have more dimensions than ours, or fewer. Some might collapse almost immediately after their Big Bang. Others might expand so rapidly that matter never clumps into stars or galaxies. Most of these universes would be lifeless, unsuitable for complexity, empty except for diffuse gas or radiation or nothing at all. But in a few, maybe a tiny fraction, the conditions are right. Stars form, planets orbit, chemistry allows for life, and in those universes, observers evolve and wonder just as we do. Why the universe seems so perfectly suited to their existence? It's speculative. We have no direct evidence for other universes. They might be forever beyond our reach, separated from us not by distance, but by some more fundamental barrier. Different space-time structures, different causal domains, realities that simply don't intersect with ours. But the multiverse idea is supported indirectly by some theories. Inflationary cosmology, which explains the uniformity and flatness of our universe, naturally produces many separate bubble universes. String theory, which attempts to unify quantum mechanics and gravity, suggests a vast landscape of possible vacuum states, each corresponding to a different universe with different properties. If the multiverse exists, then our universe isn't special. It's just one of many, selected by the fact that we can only exist in a universe where the conditions permit observers, and if the multiverse doesn't exist, then we live in a single universe, finely tuned for reasons we don't understand, and the question of why remains unanswered. Either way, it's humbling. We might be one small part of a vast cosmic ensemble, or we might be alone in a singular, inexplicably hospitable reality. We don't know which, and we might never know. The heat death of the universe is a theoretical end state, predicted by thermodynamics, where everything reaches the same temperature and no work can be done. It's based on the second law of thermodynamics. Entropy always increases. Systems move toward disorder, toward equilibrium. Hot things cool down, cold things warm up. Energy spreads out, becomes more evenly distributed, less useful. In the far future, trillions of years from now, the universe will have exhausted its energy sources. Stars will have burned out, black holes will have evaporated, matter itself might decay, protons breaking apart into lighter particles and radiation. What remains will be a cold, dark expanse, scattered photons, low-energy particles, all at nearly the same temperature, just above absolute zero. No gradients, no differences in energy, nothing to drive processes or create structure. It's called heat death, though cold death might be more accurate. The universe won't be hot, it will be frozen, featureless, unchanging. Time will still pass, but nothing will happen. No stars, no life, no events. Just a vast empty sameness, stretching on forever. It's a bleak vision, but it's also distant, so far in the future that the timescales involved are almost meaningless. trillions upon trillions of years. The universe we live in now, full of stars and galaxies and life, is just the beginning, a brief, bright phase before the long fade into darkness. But that's assuming the universe continues to expand, that dark energy remains constant or grows stronger. If something changes, if dark energy weakens or reverses, the future could be different. A big crunch, where expansion stops and reverses, pulling everything back together. Or a big rip, where expansion accelerates so much that it tears apart galaxies, stars, planets, atoms themselves. We don't know which ending awaits, but for now, heat death seems most likely. A slow, quiet fade. The universe growing dark and cold, entropy marching onward, until nothing remains but the faint whisper of energy, spread too thin to matter. Black holes don't last forever. They evaporate slowly through a process called Hawking radiation, quantum effects near the event horizon that cause the black hole to lose mass over time. It's incredibly slow. A black hole with the sun's mass would take about 10 to the power of 67 years to evaporate. That's a number with 67 zeros, longer than the current age of the universe by a factor so large it's almost incomprehensible. Larger black holes take even longer. Supermassive black holes with millions or billions of solar masses could take 10 to the power of 100 years or more. By the time they finally evaporate, the universe will be unrecognizable. Dark, cold, long past the era of stars and galaxies. But eventually they'll fade. The radiation will carry away their mass, bit by bit, until the black hole shrinks to nothing and disappears in a final burst of energy. And then they'll be gone. No remnant, no trace. Just empty space where a black hole once was. It's strange to think about. Black holes seem so permanent, so inevitable. Once something crosses the event horizon, we say it's lost forever, beyond retrieval, trapped in a gravitational well so deep that not even light can escape. But given enough time, even black holes die. Slowly, patiently, they radiate themselves away, returning their mass to the universe, obeying the same laws that govern everything else. Nothing lasts forever. Not stars, not planets, not even black holes. The universe is patient, and entropy always wins. The holographic principle suggests that all the information contained in a three-dimensional region of space can be encoded on a two-dimensional surface, its boundary. It's like a hologram. A hologram is a flat image, two-dimensional, but when you look at it, you see a three-dimensional scene. All the information about depth, perspective, the full 3D structure, it's encoded in the 2D surface. The holographic principle suggests the universe might work the same way. Everything we perceive as three-dimensional, space, matter, motion, all of reality, might be information stored on a distant two-dimensional boundary, perhaps at the edge of the observable universe, or on the event horizon of a black hole. We would be projections in a sense, not quite illusions, but patterns encoded on a surface, experiencing ourselves as existing in 3 dimensions, even though the fundamental description of reality is 2-dimensional. It sounds like science fiction, but it emerges from serious physics, string theory, quantum gravity, studies of black hole thermodynamics. The mathematics suggests that the amount of information a region of space can contain is proportional to its surface area, not its volume, which implies that the third dimension might be in some deep sense emergent, derived, not fundamental. We don't know if it's true. We don't know what it would mean for our understanding of reality if it is. but it's one of the strangest ideas to come out of modern physics. The possibility that the universe, in its deepest nature, is flat, and everything we experience is a shadow, a projection, information painted on a cosmic canvas we can never see directly. It's humbling, disorienting, and oddly beautiful. Quantum mechanics suggests that particles can exist in multiple states simultaneously, a phenomenon called superposition. An electron can be in multiple places at once. A photon can be polarized in multiple directions. A particle can spin both clockwise and counterclockwise until something observes it, and the superposition collapses into a single, definite state. It's been confirmed experimentally over and over. Quantum systems behave this way. It's not a failure of measurement or a quirk of our instruments. It's how reality works at small scales. But it raises profound questions when we think about the universe as a whole. Was the early universe in a superposition of states, multiple configurations, then multiple possible outcomes existing simultaneously until... what? Until something observed it? But there were no observers, no conscious beings, no measurement devices, nothing to collapse the wave function. So did the universe remain in superposition? Did reality split into many branches, each corresponding to a different outcome? The many worlds interpretation, where every quantum event creates new universes and all possibilities are realized somewhere? Or does observation not require consciousness? Maybe the universe observes itself through interactions, through particles affecting other particles, through decoherence, the process where quantum systems become entangled with their environment and effectively collapse into classical states without needing a conscious observer. We don't know. Quantum mechanics gives us the math, the predictions, the experiments, but it doesn't give us a clear picture of what's actually happening, what it means for something to be in superposition, why observation seems to matter. And when we scale those questions up to the cosmos, to the early universe, to the Big Bang, to the quantum fluctuations that seeded galaxies, the mysteries deepen. Maybe the universe was never in a pure state. Maybe it's been observing itself all along, collapsing possibilities into actualities through sheer interaction, through the constant exchange of information between particles and fields. Or maybe we're missing something fundamental, some deeper theory that will make sense of the strangeness, that will explain why reality seems to need observers, or why it doesn't. For now, it's a puzzle, a beautiful, frustrating, endlessly fascinating puzzle. Space and time aren't separate. They're woven together into a four-dimensional fabric called space-time, a single, unified structure where the three dimensions of space and the one dimension of time are inseparable. This was Einstein's insight, the foundation of relativity. Events don't happen in space at a certain time. They happen at specific points in space-time, locations defined by four coordinates, 3 for space, 1 for time. And space-time isn't flat. It's curved by mass and energy. Massive objects like stars and planets create dips and warps in the fabric, and what we experience as gravity is actually the effect of moving through curved space-time. Imagine a bowling ball placed on a trampoline. It creates depression, and if you roll a marble nearby, the marble curves toward the bowling ball, not because the ball is pulling on it, but because the surface is curved. That's gravity. Not a force pulling objects together, but the geometry of space-time guiding their motion. Light follows this geometry too. It travels in straight lines through space-time, but if space-time is curved, the straight lines curve with it. That's why we see gravitational lensing, light from distant galaxies bending around massive objects, creating multiple images or distorted arcs in the sky. And near very massive objects, black holes, neutron stars, space-time becomes extremely curved. Time slows down, distances distort. The closer you get to a black hole's event horizon, the more space-time warps, until at the horizon itself, space-time curves so steeply that all paths lead inward, toward the singularity, and escape becomes impossible. It's a profound shift in how we think about reality. Space and time aren't fixed backdrops against which events play out. They're dynamic, flexible, shaped by matter and energy, responding to the universe's contents, and we move through them, following the curves, experiencing gravity not as a force, but as the natural consequence of space-time's geometry. The Planck epoch, the first 10 to the power of minus 43 seconds after the Big Bang, is a realm where our physics breaks down completely. We call it the Planck time, the smallest meaningful unit of time, the point where quantum effects and gravity merge in ways we don't yet understand. At this scale, space-time itself becomes quantized, grainy, fluctuating. The smooth fabric we experience breaks down into discrete units, quantum foam, where the concepts of before and after lose meaning. We have no theory that fully describes the Planck epoch. General relativity handles large-scale gravity and curved space-time. Quantum mechanics handles small-scale particles and fields. But at the Planck scale, both theories are necessary, and they don't fit together. They give contradictory answers, infinities, nonsense. We need a theory of quantum gravity, a unified framework that combines relativity and quantum mechanics into a single, coherent description. String theory is one candidate, loop quantum gravity is another, but we don't have experimental evidence for either, and we might never have it, because the energies required to probe the Planck scale are far beyond anything we can create in laboratories. So the Planck epoch remains mysterious. The earliest moment, the beginning of time, the birth of the universe, locked behind a wall of ignorance, accessible only through speculation and mathematics. What happened then? We don't know. Did time itself emerge from something more fundamental? Did the universe begin in a singularity, a point of infinite density? Or was there no beginning, just a transition from one state to another, a quantum fluctuation that gave birth to space-time? The answers, if they exist, are hidden in physics we haven't discovered yet. And maybe that's appropriate. The origin of everything should be mysterious, should challenge us, should remain just beyond reach until we've deepened our understanding enough to grasp it. Cosmic inflation theory suggests that the universe expanded exponentially in the first fraction of a second after the Big Bang, growing from smaller than an atom to larger than a galaxy in less than a trillionth of a second. It sounds absurd, but inflation solves several problems with the standard Big Bang model. The horizon problem. Why is the cosmic microwave background so uniform? Distant regions of the universe have the same temperature, even though they're too far apart to have ever communicated, to have ever exchanged heat and reached equilibrium. Inflation explains this. Before inflation, those regions were close together, in contact, able to equilibrate. Then inflation stretched them apart faster than light, preserving the uniformity, the flatness problem. Why is the universe so close to geometrically flat? Slight deviations from flatness should amplify over time, making the universe either strongly curved like a sphere or strongly curved like a saddle. But it's remarkably flat. Inflation explains this too. Rapid expansion smooths out curvature, the way inflating a balloon smooths out wrinkles, and inflation explains the origin of structure. Tiny quantum fluctuations, subatomic variations in density, were stretched by inflation to cosmic scales, becoming the seeds for galaxies, clusters, the cosmic web. Without inflation, we wouldn't have a good explanation for why matter isn't distributed perfectly evenly, why there are dense regions and voids. But we don't know what caused inflation. Some field, some energy, triggered the expansion and then decayed, ending inflation and transitioning the universe into the slower, decelerating expansion we observe today. We call this hypothetical field the inflaton, but we don't know what it is, where it came from, or why it behaved the way it did. Inflation is a theory that explains a lot, but it raises new questions, deeper mysteries, about the origin of the inflaton, the nature of the pre-inflationary universe, whether inflation happened once or is happening eternally in other regions of space, creating bubble universes in an endless multiverse. We have evidence consistent with inflation, patterns in the cosmic microwave background, the distribution of galaxies, but we don't have proof, and we might never have it because the Planck epoch where inflation occurred might be forever beyond our ability to observe directly. Still, it's our best explanation. A moment of exponential expansion, a cosmic blink that set the stage for everything that followed. The universe might be flat, curved like a sphere, or saddle-shaped, 3 possibilities, each leading to different ultimate fates. A flat universe expands forever, gradually slowing but never quite stopping. Galaxies drift apart, stars burn out, eventually heat death, cold, dark, empty. A spherical universe has positive curvature, like the surface of a ball. In this case, the universe's expansion might eventually halt and reverse, pulling everything back together in a big crunch, the opposite of the Big Bang, a collapse into a singularity, everything compressed into an infinitely dense point. A saddle-shaped universe has negative curvature, like a Pringle chip. It expands forever, accelerating, galaxies receding faster and faster until they're beyond each other's cosmic horizons, isolated, alone. Current observations suggest the universe is very close to flat, so close that we can't yet measure any curvature. If it's exactly flat or close enough, then the expansion will continue forever, eventually leading to heat death or, if dark energy grows stronger, a big rip where accelerating expansion tears apart galaxies, stars, planets, atoms, everything. But we're not absolutely certain. Curvature could exist on scales larger than we can observe, beyond the horizon of the observable universe. The geometry we measure might be local, not universal. For now, flatness seems most likely. A universe that expands eternally, growing darker and colder, until the last stars fade and the last black holes evaporate and nothing remains but scattered particles too far apart to ever interact again. It's a lonely ending, but it's billions upon billions of years away, so distant that it feels almost abstract, irrelevant to the universe we experience now, vibrant with stars and galaxies and life. Vacuum energy, the energy inherent in empty space, might be responsible for dark energy and the accelerating expansion of the universe. Quantum mechanics tells us that empty space isn't truly empty. It seethes with virtual particles, fluctuations in quantum fields, constantly creating and annihilating particle-antiparticle pairs in tiny bursts of energy. This vacuum energy should exert a kind of pressure, a repulsive force that pushes space apart. And that might be what dark energy is. The energy of the quantum vacuum, a property of space itself, constant and unchanging, causing the universe to expand faster and faster. But there's a problem. When physicists calculate how much vacuum energy should exist, they get an answer that's about 120 orders of magnitude larger than what we observe. That's not a small discrepancy. It's one of the worst predictions in the history of physics. Either the calculation is wrong, missing some cancellation mechanism, some principle that reduces the vacuum energy to the tiny value we measure, or vacuum energy isn't the explanation for dark energy, and something else is driving the acceleration. We don't know which. The vacuum energy problem remains unsolved, a reminder that despite all our progress, despite relativity and quantum mechanics and the Standard Model, we're still missing fundamental pieces of the puzzle. Space itself might have energy. Empty space might weigh something, might push against gravity, might determine the fate of the universe, but we don't understand why, or how, or what it means. For now, it's a mystery, one of many, scattered through the foundations of physics, waiting for new insights, new theories, and new ways of looking at the cosmos. The cosmic horizon problem asks why distant regions of the universe that couldn't have ever communicated, regions too far apart for light to have travelled between them, have the same temperature, the same properties, the same structure. If the universe expanded at a constant rate since the Big Bang, then there are regions of space that have never been in causal contact. Light from one region hasn't had time to reach the other. They've been separated since the beginning, unable to exchange information, unable to equilibrate. And yet, when we measure the cosmic microwave background, it's almost perfectly uniform. This same temperature in every direction, varying by only 1 part in 100,000. How did these disconnected regions end up so similar if they've never interacted? May cosmic inflation provides an answer. Before inflation, the regions were close together, in contact, able to reach the same temperature. Then inflation stretched space exponentially, carrying them apart faster than light, preserving the uniformity they'd already achieved. It's an elegant solution, but it raises new questions. What caused inflation? Why did it start? Why did it stop? And if inflation can happen once, can it happen again, elsewhere, creating other bubble universes, an endless multiverse? We don't have all the answers, but the horizon problem and inflation's resolution of it is one of the strongest pieces of evidence that something strange and dramatic happened in the first fraction of a second, something that shaped the universe we see today. Primordial black holes might have formed in the first second after the Big Bang, where regions where density fluctuations were strong enough to collapse directly into black holes without needing a star to die first. These wouldn't be stellar mass black holes. They could be much smaller. Some might weigh as much as a mountain, compressed into a volume smaller than an atom. Others could be larger, perhaps large enough to account for some of the mass we attribute to dark matter. We've never confirmed their existence, but they're allowed by physics, and they could be scattered through the universe, invisible relics from the earliest moments, drifting through space, affecting galaxies through their gravity but otherwise undetectable. If primordial black holes exist, they could explain some puzzles. They might be the seeds around which the first galaxies formed. They might contribute to dark matter, or even account for all of it, eliminating the need for exotic particles. Or they might not exist at all. We don't know. They're a possibility, a hypothesis, one of many ideas about what might be hiding in the dark, The universe is full of things we can't see. Dark matter, dark energy, potentially primordial black holes, and we're left to infer their existence from gravitational effects, from patterns in the cosmic microwave background, from the way galaxies move and cluster. It's like trying to understand a room in the dark, feeling your way around, bumping into furniture, mapping the space by touch alone. Slowly, we're building a picture, but there's still so much we can't see, can't touch, can only guess at. Yeah, the universe's fine structure constant, a number that determines the strength of electromagnetic interactions, appears perfectly calibrated for complex chemistry. If it were just a few % different, stars couldn't produce both carbon and oxygen, the elements essential for life as we know it. Too strong and carbon would be unstable, too weak and oxygen wouldn't form. The window is narrow, and we happen to exist in a universe where the value falls right in the middle, allowing for the chemistry that makes planets, atmospheres and biology possible. Is this fine-tuning evidence of design? Some people think so, a universe deliberately constructed to allow for life, or is it selection bias? If there are many universes, we naturally find ourselves in one where the constants permit observers. The others exist, but they're empty, lifeless. And no one is there to notice them. Or is it a coincidence? Just luck, a random configuration that happened to work out in our favour? We don't know. The fine structure constant is what it is. We can measure it, use it in calculations, build technology based on electromagnetic interactions. But we can't explain why it has the value it does, or whether other values are possible, or what it means that we exist in a universe where everything seems just right. It's one of the deepest questions in physics, and the answer, whatever it is, will tell us something profound about the nature of reality. We are made of stardust, literally. Every atom in your body except hydrogen was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, is the carbon in your DNA. All of it came from stars that exploded billions of years ago, scattering their contents into space, seeding the clouds that would eventually collapse to form the sun and planets. Hydrogen is the exception. It's primordial, left over from the Big Bang, part of the original material of the universe. But everything heavier, helium, carbon, oxygen, nitrogen, phosphorus, sulfur, all the elements that make up life, those were made in stars, through fusion, through supernovas, through the violent processes that accompany stellar death. You are ancient. The atoms in your hand are older than the Earth, older than the Sun. They've been recycled through multiple generations of stars, each one adding a bit more complexity, a bit more diversity, until eventually they found their way into a molecular cloud, and then into the solar system, and then into the planet, and then into life. And when you die, those atoms will return. They'll be recycled again, incorporated into soil, into plants, into other organisms, or scattered into the atmosphere, carried by wind and rain to distant places. Nothing is truly created or destroyed, just rearranged, transformed, passed from one form to another in an endless cycle. We are temporary patterns in the flow of matter, brief configurations of stardust that happen to be conscious, able to wonder about our origins, able to look up at the night sky and recognize that we are part of it, made from it, connected to the cosmos in the most fundamental way possible. It's humbling and beautiful and true. The observable universe contains about 10 to the power of 80 atoms. That's a 1 followed by 80 zeros, a number so vast it exceeds comprehension. If you counted 1 atom per second, never stopping, it would take you far longer than the age of the universe to count them all. Longer than the universe will exist, probably, before heat death or some other ending. And yet for all those atoms, most of the universe's mass remains invisible. Dark matter, which doesn't form atoms at all, but exists in some other form we don't understand. 10 to the 80th atoms, scattered through galaxies, stars, planets, gas clouds, drifting alone through intergalactic space. Some are part of living organisms, bacteria, plants, animals, you. Most are not. Most are hydrogen or helium, part of stars or nebulae fusing and radiating or just drifting inert. And every one of them has a history. They were created in the Big Bang, or in the cores of stars or in supernovas. They've travelled, collided, bonded with other atoms, broken apart, recombined. Some have been part of planets that no longer exist, stars that exploded, moons that shattered. The atoms in your body have histories we can't trace. Journeys we can only imagine. They've been recycled countless times, part of countless structures before becoming part of you. And they'll continue after you're gone, moving on to new configurations, new roles, new stories, until the universe itself fades and the atoms disperse into a cold, dark expanse where nothing ever changes again. For now, though, they're here. Part of you. Part of the living, breathing, thinking universe, experiencing itself. Einstein's equations suggest time travel to the future is possible, and it's been demonstrated with atomic clocks. Clocks on fast-moving aircraft run slower than stationary clocks. GPS satellites, orbiting at high speed in weaker gravity, experience time differently and must adjust for it. But travelling to the past is more problematic. It creates paradoxes, loops in causality, events that could prevent their own cause. You could travel back and prevent your own birth, or kill your grandfather before your parent was conceived. The universe seems designed to prevent such contradictions. Some solutions to Einstein's equations allow for closed time-like curves, paths through space-time that loop back on themselves, theoretically permitting travel to the past. But they require exotic conditions, rotating black holes, wormholes held open by negative energy, space-time geometries we've never observed, and they might be impossible. Some physicists argue that quantum effects, or unknown principles of physics, would prevent closed time-like curves from forming, preserving causality at all costs. Others suggest that time travel to the past might create new timelines, branching realities where the paradoxes are resolved by splitting the universe. You can't change your own past, but you can enter a parallel timeline where events unfold differently. We don't know. Time travel to the future is easy. Just move fast or stay near a strong gravitational field. But time travel to the past remains speculative, theoretical, possibly forbidden by laws we haven't fully discovered yet. For now, we're stuck moving forward, 1 second at a time, unable to revisit the past or skip ahead except through the slow, steady march of time. The cosmic web structure, filaments of galaxies surrounding vast voids, resembles neural networks in the brain. It's a coincidence, probably, but a striking one. The largest structures in the universe and the smallest networks in our heads, both organizing themselves into similar patterns. Maybe it's not surprising. Both systems are shaped by optimization, by efficiency, by the way connections form and information flows. Neurons connect to nearby neurons, forming clusters and pathways. Galaxies cluster along filaments, drawn together by gravity, creating networks of matter. The patterns are similar because the underlying principles, connectivity, clustering, the balance between local and global structure, are universal, applying to systems across vastly different scales. Or maybe it's deeper than that. Maybe the universe, at every level, favours certain organisational principles, certain ways of structuring complexity. Fractals appear everywhere, in coastlines, in snowflakes, in the distribution of galaxies. Self-similar patterns, repeating at different scales. The universe might be fundamentally fractal, or at least prone to creating fractal-like structures, because the laws of physics favour them, because they are efficient, because they emerge naturally from simple rules applied over time. We don't fully understand why these patterns appear, but they do, from the smallest to the larger scales, hinting at deep connections between different realms of existence, between the structure of thought and the structure of the cosmos. Despite all our knowledge, 95% of the universe consists of dark matter and dark energy, substances we don't understand, and forces we can't explain, mysteries that dominate the cosmos. We've mapped the universe, catalogued billions of galaxies, detected gravitational waves, imaged black holes, traced the cosmic microwave background. We've learned an astonishing amount in the past century, and yet the overwhelming majority of the universe remains unknown. Dark matter holds galaxies together, shapes the cosmic web, influences the motion of stars and clusters. But we don't know what it is. Dark energy drives the accelerating expansion, determining the ultimate fate of the universe. But we don't know what it is either, 95%. We're like explorers who've mapped 5% of a continent, leaving the rest blank, marked unknown. We have theories, guesses, ideas, but we don't have answers. It's humbling and exciting, because it means there's so much left to discover, so many mysteries waiting to be solved, so many questions we haven't even learned to ask properly yet. We're in the early stages of understanding the cosmos. We've made remarkable progress, but we're still beginners, still learning, still scratching the surface of what's out there. And maybe that's how it should be. The universe is vast, ancient, complex beyond imagining. It would be strange if we'd figured it all out already, in just a few centuries of serious scientific inquiry. There's more to learn, always more. And that's a gift in its way, an invitation to keep exploring, keep questioning, keep reaching for the stars. Every time you look up at the night sky, you're seeing into the past. Starlight carries ancient photons from distant times and places, travelling across the void to reach your eyes. The light from the sun is 8 minutes old. The light from Alpha Centauri, 4.37 years old. The light from stars across the galaxy, tens, hundreds, thousands of years old depending on distance. And when you look at distant galaxies, Andromeda for instance, visible to the naked eye on dark nights, you're seeing light that left 2.5 million years ago. Before humans evolved into our current form, before the last ice age, the light has been travelling through space all that time, and it's only now reaching your eyes. The universe is a time machine. The farther you look, the further back in time you see. Telescopes are history books, revealing the cosmos as it was, not as it is. And that means the stars you see might not even exist anymore. Some of them have died, exploded, faded into white dwarfs or collapsed into black holes. But their light continues, carrying the image of what they once were, crossing the galaxy, preserving their memory long after they're gone. It's haunting, in a way. Beautiful, too. The night sky is a museum of ghosts, a collection of images from the past, assembled by light that has travelled unimaginable distances to tell us stories about distant places, distant times, and we're part of that story. Our light, the light reflected from Earth, the radio waves we've broadcast into space, is travelling outward, carrying information about us to whoever might be watching, decades or centuries or millennia from now. We're all ghosts in the end, images travelling through space-time, reflections of what we were long after the moment has passed. Some planets orbit in the habitable zone, the region around a star where temperatures are right for liquid water, where life as we know it could potentially exist. Not too close, where water would boil away, not too far where it would freeze solid, just right, in the narrow band where oceans could form, where chemistry could become complex, where biology might take hold. We've found thousands of exoplanets now, and some of them orbit in habitable zones, rocky worlds, roughly Earth-sized, receiving the right amount of starlight to maintain liquid water on their surfaces. We don't know if they actually have water. We don't know if they have atmospheres, or magnetic fields, or any of the other conditions that might make them truly habitable. We can measure their size, their distance from their star, their orbital period, but we can't see their surfaces, can't analyse their air, can't determine whether they're oceans or deserts or something in between. Still, the potential is there. Worlds where life could exist, scattered throughout the galaxy, orbiting distant suns, waiting. Maybe some of them are inhabited. Maybe life arose independently, following different paths, creating ecosystems and biospheres utterly alien to ours. Or maybe they're barren, sterile, full of potential but empty of realization. We don't know. We're searching, analysing starlight, looking for biosignatures, oxygen, methane, compounds that might indicate biological processes, but we haven't found anything conclusive yet. The habitable zone is just that, habitable, not inhabited, not guaranteed to produce life, just capable of supporting it, if the conditions are right. If chemistry follows the right pathways, if chance and time and complexity align in just the right way. It's a start though, a place to look, a reason to hope that somewhere out there, on a world we haven't named yet, orbiting a star we've barely noticed, something is alive, looking up at its own night sky, wondering the same things we wonder. Comets occasionally bring water and organic molecules to planets, seeding them with the building blocks of life. Earth might have been enriched this way, bombardment by comets in its early history delivering the oceans and the chemistry that would eventually lead to biology. If that's true, and we think it might be, then life on Earth has cosmic origins, assembled from materials that travelled across the solar system, forged in the cold outer reaches and delivered by impacts to a warm young world. And if it happened here, it could happen elsewhere. Comets don't discriminate. They fall on Mars, on Europa, on moons and planets throughout the solar system and beyond. Wherever they land, they deposit their cargo, ice, organics, the raw ingredients for complexity. Maybe life is common, seeded wherever conditions permit, scattered by comets like seeds in a cosmic wind. Or maybe it's rare, requiring not just the ingredients, but also the right environment, the right sequence of events, the right combination of chance and necessity. We don't know. But every time a comet streaks across the sky, it's worth remembering that these ancient icy visitors aren't just beautiful. They're messengers, carriers of material that might, under the right circumstances, become something more, something alive. The sun converts 4 million tons of matter into pure energy every single second, yet it still has enough hydrogen to shine for another 5 billion years. 4 million tons every second, simply ceasing to exist as matter, becoming light and heat instead, radiating into space according to E equals mc squared. And despite this staggering rate of consumption, the sun has barely changed over its 4.6 billion year lifetime. It's slightly brighter now than when it formed, but otherwise stable, reliable, constant. It will continue this way for billions of years more. Slowly it will brighten as helium accumulates in its core, altering the fusion dynamics. Eventually it will swell into a red giant, growing hundreds of times larger, swallowing the inner planets. But that's far in the future. For now, the sun burns steadily, converting mass to energy. See, warming our world, driving photosynthesis, powering weather and ocean currents in the entire biosphere. We take it for granted, the way we take breathing for granted. The sun is just there, rising and setting, predictable and constant. But every ray of sunlight represents atoms destroyed, mass converted to energy, a tiny piece of the sun sacrificed to keep the fusion going. 4 million tons per second. And it's not even close to running out. The sun is generous, patient, steadfast, and we are its children, living in the narrow band of temperature and light it provides, utterly dependent on its continued burning. For 5 billion more years, it will shine, and then it will change, transform, die in its own way. But for now, it endures, our star, our source, the centre around which everything revolves. Space is not empty. Space is not silent. Space is not still. It's full of light, starlight, cosmic microwave background, radiation from every wavelength travelling through the void, carrying information about distant places and ancient times. It's full of particles, cosmic rays, neutrinos, solar wind, atoms drifting between stars, ions accelerated by magnetic fields, the thin remnants of stellar explosions scattered across light years. It's full of fields, gravity, electromagnetism, quantum fields fluctuating at every point, creating and annihilating virtual particles in the vacuum, humming with energy we can barely detect. And it's full of motion, galaxies rotating, stars orbiting, planets spinning, the universe expanding, space-time itself stretching, carrying everything along in a vast, slow current that never stops. Space is alive with activity, rich with phenomena, dense with mystery. It's not a void. It's a medium, a fabric, a stage on which the universe performs its endless dance of creation, destruction, light and dark, order and chaos, and we are part of it, made from it, connected to it in ways we're still discovering, still understanding, still learning to appreciate. Every time you look up at the night sky, whether you see stars or clouds or city lights, you're looking at the edge of everything. The boundary between here and there, between now and then, between the familiar and the unknown. Space is waiting, full of wonders we've barely begun to explore, full of questions we've barely begun to ask. And somewhere in that vastness, in the darkness between the stars, there might be answers. There might be others looking back, wondering the same things. Or there might be only silence, only light, only the slow turning of galaxies in the dark. Either way, we're here, conscious, curious, awake in a universe that doesn't require our presence but somehow permits it. that doesn't need observers but somehow produces them. We're here, looking up, wondering, and that in itself is a kind of miracle. And so we've travelled together through space, not the empty void we once imagined, but a cosmos full of light and motion and mystery, where every observation raises new questions, where every answer reveals deeper puzzles. 100 facts, and we've barely scratched the surface. There are billions of galaxies we haven't mentioned, trillions of stars whose stories remain untold, planets and moons and phenomena scattered across distances so vast that numbers lose meaning. But perhaps that's the point. The universe is not meant to be fully known, fully catalogued, fully understood. It's meant to inspire wonder, to invite curiosity, to remind us how small we are and how much remains to discover. We are made of stardust, temporary patterns in the flow of cosmic matter, brief sparks of consciousness in an ancient universe. We didn't ask to be here, but here we are, thinking, questioning, reaching toward the stars with telescopes and mathematics and dreams. And maybe that's enough. Not to know everything, but to keep asking. Not to solve every mystery, but to appreciate that mysteries exist. Not to conquer space, but to wonder at it, to let it fill us with awe. The night sky is still there, waiting. The stars still shine, carrying light from distant times, and somewhere in the vast dark, perhaps someone else is looking up, wondering the same things, feeling the same pull toward the infinite. Or perhaps we're alone, the only eyes the universe has opened to see itself, the only minds it's shaped to ask why. Either way, we're part of something larger, something ancient and beautiful and strange, something worth contemplating as you drift towards sleep, letting the vastness wash over you, letting the mysteries settle into your thoughts like stars settling into the night. Rest well. The universe will still be here tomorrow, full of wonders, full of questions, full of light travelling through the dark, waiting for us to notice, and we will. We always do. Good night.